Does it work properly, okay?
I think so.
Okay.
Carlos, can you hear? Try again.
Hello? Does it work? Okay. Okay.
start our morning session. The first talk will be of David Paluara, massive, massless, what is this letter, sorry?
Dressing factor. Is a E.
Okay, dressing factor for mixed flux ADS3, S3, T4, please.
Okay, first of all, let me thank the organizer to have invited me to be here. I'm very happy for this edition of IGST. Let me also give a quick announcement. I took the umbrella of someone else yesterday and I left it here, so you're free to claim it back. My talk will be indeed about massive and massless dressing factors, and is based on working collaboration with Sergei Frolov and Alessandro Sfondrini. The past years, Alessandro Sfondrini gave a similar talk actually in São Paulo, and I think Bogdan gave a similar talk in IDD at that time. And now we are here together, so we can actually fight for. But what it is about? It's about string theory in this background, ADS3, S3, T4, in the presence of mixed flux. And this is a family of classicable integrable model, which is defined by two free parameters, which is the amount of Nevers-Warth flux and Ramon-Ramon flux. And I will label this by these two parameters. K is an integer, which can be 0, 1, and so on and so forth, while H, which is the amount of Ramon-Ramon flux, is bigger or equal to 0. And sum is known. For example, if you take H equal to 0, exactly equal to 0, then the worksheet strings is defined by a Vezumino-Witten model on this worksheet. And this can be studied by conformal field theory method. And also in the case in which you have a minimal amount, for example, of an SNX flux, and you eventually deform by introducing some small amount of Ramon flux around this background, the dual conformal field theory, there is a proposal which comes from Eberhard, Gaberdi, and Gupta-Kumar, and people studied on the CFT side what this should correspond to. But as we turn on a big amount of H, so we have a big amount of Ramon flux, this conformal field theory method kind of fall down. And we believe the most useful thing is to study the theory by integrability. And a lot of progress has been done in the past year in the case in which you have exactly K equal to 0, so no NSNS flux, but just Ramon-Ramon. And there have been different groups that have studied these theories either from the worksheet perspective and tried to derive what are the thermodynamic beta ansatz for the pure Ramon-Ramon case. In particular, Frolov and Sfondrini derived these equations, and there was also some studied, numerical studied. Many people in this audience instead derive directly some quantum spectral curve. So there is still some gap between thermodynamic beta ansatz and quantum spectral curve. In ADS5, S5, this has been a derivation through Y system, TQ relation. It is a non-trivial derivation to connect these two. But in principle, you can also bootstrap some quantum spectral curve, and from the proposal of the quantum spectral curve, try to take some large volume limit. And as a consistency check that the equations are correct, these people in particular, the last paper comes from Ekhammar, Gromov, and Stefanski, re-derived what are the dressing factor of S matrix. So this is a kind of consistency check that everything should work fine. But what I would like to speak about today is the case in which both H and K are non-equal to 0, okay? So in principle, you have some worksheet S matrix, which is known by imposing that it should commute with the supercharges of your theory. What it is not known is an overall multiplicative factor in front of S matrix. So any scalar factor that you put in front of S matrix, of course, does not modify the commutation relation. And this additional factor is something we need to check and we need to fix by requiring additional properties. For example, unitarity, crossing, fusion, and dates back to Zamologikov and Zamologikov, in which you should use the bootstrap method to fix what is this basically factor. Okay? So a proposal for this, at least part of the solution for this dressing factor, comes also in this paper by Olson, Sak, Ryabichenko, and Stefanski. What I will try to tell you is the part which is missing basically in this paper. So there is a proposal which fixes part of this factor. What is not fixed is the part which involves the BS phase, and this is what I want to talk about mainly today. So the plan is mainly looking at the massive part of S matrix, and in this case I will look at the crossing equation in the case in which you have K equal to 0, so just Ramon-Ramon, And then I will look at the case in which k is different from 0 and you have indeed this mixed flux. I will also mention about massless particles, but since I don't have much time, I think that the massive case anyway contains more or less all the information of your theory, and you can generate then the massless S matrices as a particular limit of a massive one. So I'm happy to discuss more if someone wants to chat about the massless S matrices, but in this talk I will mainly focus on the massive ones, okay? So what are the massive particles of my model? They live in short representation of this gauge-fixed supersymmetry algebra. There are some left particles, this is a left representation, and in the dispersion relation, we connect the energy as a function of a momentum. P is my worksheet momentum. They appear the amount of NS and S flux, so this K, which is a quantized number, and this H, which is the amount of Ramon fluxes. In the other one, in the other representation involving a right particle, and somehow these particles are the charge conjugate of these ones. So if you have Y, which belongs to some left representation, then you will have some Y bar belonging to the right representation, okay? Each particle here contains an antiparticle in the other representation, and particle and antiparticle are connected by the fact that on one side, this K, the amount of NS and S flux, comes with the plus sign, on the other side comes with the minus sign. So swapping the sign of this NS and S flux connect particles with antiparticles. So what I want to fix are these dressing factors. So I should say that within this multiplet you can scatter, the theory is integrable, so you can have a mixing between left and right particles or mixing within the same multiplet, but at the level of representation the scattering is purely elastic. So if you start with two left particles, they scatter to each other but remains in the same representation, left. So in principle you have 4 different dressing phases which are not fixed by symmetry, corresponding to the scattering of left, 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 right, right, left, and right, right. Okay, and this is what I want to fix, and I'll try to fix in this talk. And the idea is that we want to fix an S matrix both in the string and in the mirror region. So how does it work in ADS5? Normally people work out this first in the string region, where tau and sigma are my worksheet coordinates. And after you find the S matrix in the string region, you would like to analytically continue to the mirror region, in which you do some double-wick rotation in such a way that after this double-wick rotation, you get some mirror theory, which in principle is different from the theory you started from. And the reason why we are interested in doing this is that in the mirror region, basically what Zamologic will teach us is that if you have some finite volume theory, this is equivalent to a theory in which the volume is infinite, but you have some finite temperature, which is exactly the inverse of the worksheet of a string. And this should keep into account of the wrapping correction and allow you to quantize the string. But the idea is that you want some S matrix, so this is a double-wick rotation, so energy and momentum on the string correspond to momentum and energy in the other theory. And if the theory is not relativistic, like in this case, you start with some dispersion relation, where you have some energy E connected to the momentum of the worksheet in this way. M is a bound state number, so M is equal to 1 for fundamental particle, that can be 2, 3, 4, 5, etc., etc. After you do this double-wick rotation, due to the fact that this dispersion relation has this form, you turn now in a dispersion relation which is non-real anymore. So on the right-hand side, you see if P tilde, which is the worksheet momentum in the mirror theory, say, is real, then the energy cannot be real too. So you start with a unitary theory, a well-defined S matrix, and you end up with a theory which is non-unitary in principle anymore. But still, if you have some string S matrix and you want to connect to some mirror S matrix, we believe that this can be done by some analytic continuation, and this is what actually we do. We derive some S matrix, and we are able to continue from one region to the other. And there are certain properties that must hold on both sides of this analytic continuation. For example, braiding unitarity. Okay, braiding unitarity is a relation which connects some S matrix at P1, P2 with another one at P2, P1. This is a relation which can be analytically continued. But for example, unitarity is not a relation which can be analytically continued everywhere. And indeed, on the mirror side, this property fails down. And similarly, if you have, in the mirror theory, parity is a property which is preserved, after you do this double-wick rotation, we should map to some time reversal symmetry. So the mirror theory, the string theory, sorry, is time reversal, but it's not anymore parity invariant. And these are all checks that should be done on all these properties that we know to be valid at the level of the Lagrangian when you do this double-wick rotation. So we would like to preserve at the level of the S matrix too, okay? So let me just discuss what it is crossing. So crossing is one of these properties that I listed here that must hold on both sides of a correspondence, and I say it later because I want to discuss now about the crossing equation. And the idea is that if you have a pure Ramon background, so this is most similar to ADS5S5, you need to solve some inverse of this Zukowski map. And I will try to solve the theory, by the way, on the mirror theory side instead of a string theory side, and eventually analytically continue back to string theory afterward. So you can do this on both sides of this correspondence. And there are two solutions to this equation. One solution contains the imaginary part of x, which is less than 0, and the other solution contains the imaginary part of x, which is bigger than 0. Of course, if x solves this equation, 1 over x also solves the same equation. And in principle, if you look at how it is done, the u-plane, you have some u-plane with long cap between minus infinity and minus 2 and plus 2 plus infinity. And doing a crossing transformation corresponds to start with some u, you cross one of this cut and end up with the same point u. And under this transformation, x tilde of u, which originally is below, is on the negative side of the complex plane, comes above and becomes 1 over x tilde of u. This is what happens in the pure Ramon case. And under this transformation, if you look at how the energy and momentum are parameterized in terms of these Zukowski variables, where I label x tilde plus minus in this way, where h is my amount of Ramon flux, you have that under this crossing transformation, energy and momentum change sign, okay? So what happened? If I look at the S matrix, I normalize the S matrix in this particular way. As I was saying before, there are 4 possible representations of your theory, which are 4 possible dressing phases, right, right, left, right, right, left, and left, left. Here I normalize the scattering of 2 right particles, Z bar, and the scattering of a left and a right particle, Y and Z bar, okay? And the reason why I don't look at the other 2 is because they are connected by left-right symmetry. As I was saying before, in principle, when you swap the sign of k to minus k, you should map Z bar, which is the scattering between right particle, to the scattering of 2 Z particles. And in the pure Ramon case, since k is equal to 0, these 2 are exactly equal to each other, okay? I put this prefactor here, which should take into account the fact that Z bar should form bound state. So this is just something that I introduce in my normalization in such a way to have the correct pole structure into the S matrix. And these 2 free functions are my dressing phases, okay? Everything I'm doing has already been done for Ramon, so here I'm just fixing some normalization, which is there also in the pure Ramon, okay? This is a pure Ramon in the mirror region. What are the crossing equations then? The crossing equation takes this particular form. So there is a red part, which is called odd part of the crossing equation. The reason why it is called odd part is because if you cross 2 times the left-hand side, this part changes, while this blue part does not change. It is called even part. And somehow this even part is an artifact of the fact that I put exactly this factor here. If I would have not put any pole in my normalization, then you just don't have this part. So somehow it seems trivial. But we also know that this even part is what contains somehow the interesting dynamics of the theory. And the BS dressing factors should be something that generates this particular part of the crossing equation. So I split the solution into some red term, which solve the odd part of the crossing. And this was shown, for example, in the paper by Alessandro Sfondrini and Sergei Frolov to be written, that can be written the solution in terms of particular gamma variable, which were originally introduced by Torrielli and Andrea Fontanella, I think. And this even part of the crossing equation is solved instead by some ratio of BS and Hernandez-Lopez. So what is the minimal solution for the odd crossing equation? As I was saying before, you introduce some gamma variable, which are connected to the Zukowski in this particular way. And then in terms of this gamma variable, you define some ratio of Barnes. So these are particular functions. Barnes gamma function can be written as infinity product of standard gamma. And even if it may look quite ugly, the kernel is quite simple for these functions R. In particular, if you derive the log of R respect to Z, you obtain something like Z cotangent of Z. It's something very simple, the kernel. And this odd part of the crossing equation is solved in terms of this R function, whereby gamma tilde minus minus, I mean gamma tilde 1 minus minus gamma tilde 2 minus, where I'm using this convention here, okay? So now let me go to the crossing for k different from 0, and I postpone the discussion of BS and Hernandez-Lopez to the k generic. In the case in which you have different k, by the way, I still have 15 minutes. 15 minutes, okay. In the case in which k is different from 0, I think this map anyway was introduced originally in this paper. I'm not sure who was the first one, introducing by Stefanchuk and Zeitlin. You have two different Zukowski maps. One is for the left particle, where k, the amount of an SNS, comes with a minus sign, and one for right particle, in which this sign comes with a plus. And in this case, you have two different solutions, okay? You can have that if x left solve the first equation, the equation number A, 1 over x left solve equation number B, because under the inversion, the log change sign, and this is a trivial fact. So you have a different solution. One, the solution of equation number A, say, is x left and 1 over x right, and the solution of equation number B is x right and 1 over x left. So you need to keep this distinct label for left and right particle. And if in the case k equal to 0, after you cross this long cut, you end up in 1 over x. In this case, in which you have k different from 0, again, you cross this long cut, which is the analog of a cut plus 2 plus infinity. And from x left, you end up in 1 over x right. This is a bit of a message. So what we are doing, you start with some energy and some momentum of a left particle. And after doing a crossing transformation, you end up to having minus the momentum and minus the energy of a right particle. So this is the idea. So when you want to construct something which scatter trivially with all the state of your theory, you need to put together some particle, some antiparticle with opposite energy and opposite momentum. This transformation is what connects the energy of a momentum of some particle with the negative of a momentum of energy of an antiparticle. What I do now, I fix some S-matrix normalization exactly in the same way as I was fixing for the poor Ramon case. I just need to put some label. Okay? Before there are no label. Zukowski were all the same. Here I put right and left in correspondence to the correct particle. If y is a left particle, it means that I'm scattering x1 left, and z bar is a right particle, I scatter x2 right. And then again, I have exactly the same type of crossing equation. There is some odd part, which is a part which was solved by Bogdan and collaborators. And then there is this even part, which we solved by proposing a particular combination of BS and Hernandez-Lopez. So again, I split the solution into these two terms. How do I solve this odd part? The way in which we solve it, it is basically the same solution, but Stefanski and collaborator propose as an integral, while we propose as this particular combination of bars, but you can check numerically that they agree. And the idea is that you promote this gamma tilde variable, which originally has branch point at -1 and +1. And now, after you introduce k, these branch points move a little bit. So there is this parameter S, which is this particular combination. As you can see, if k becomes 0, this is exactly 1. But if k is different from 0, you have this different proposal for gamma left and gamma right. And then what you do, you take the solution for the Ramon case and just replace gamma 1. And this should have been a gamma 2, by the way, but okay, you substitute instead of gamma 1 and gamma 2, gamma right 1 and gamma right 2, depending on what dressing factor are you looking at. But it's basically some smooth formula in which you want to generalize to this case. While for the even solution that we solved in mirror theory, we use the Dory-Hoffman-Maldacena representation of improved BS dressing factors, in which basically the improved BS dressing factor can be written in terms of these building blocks as an integral in the x-plane, which runs over the real line. What is the real line is the boundary between what it was the mirror and anti-mirror region. Okay? So this representation in this way for the mirror theory, I think, was used for the first time by Gromov, Kozak, and Vieira. And what we want to do is to generalize this case to the mixed flux. Okay? So in this case, you have that case different from 0. So what happens? It happens that u, as a function of x, contain a log cut. So you need to decide if that representation runs as an integration path, which runs below the cut of the log, or above a cut of a log. So you can have different combination of these phi function with different possibility for your boundary. And in this case, you need to put some label, A and B, which correspond to left and right and left particle, which enter these U's. As we were saying before, U left comes with a plus K over H, and U right was entering with minus K over H. Okay? Sorry, it's the opposite, but anyway, there is a sign difference between left and right. And then you need to decide your boundary. And I define this boundary to be plus of minus. Minus corresponds to run below the real line and plus above the real line. And it turned out that the only possibility to have a solution which is compatible both with crossing and with parity of a model is the case in which if you have two particles of the same time, they can be right or both left, you must have the same type of contour. So it can be minus minus or plus plus. And if you have particles of different types, like left right, you have opposite contour in the solution of a crossing equation. Of course, this in the limit in which K becomes 0 becomes the standard building block for the improved BS dressing factor, okay? And this turned out to agree also perturbatively. So if you take a large string tension and you take this particular combination, is something that reproduces exactly the FS order and the perturbative computation at 3 levels at least. So the proposal for our K-deform improved BS dressing factor is this one, in which you take this building block, and then you have different phases depending if you scatter left, 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 right, and so on and so forth. And to read off the Hernandez-Lopez order of this phase, you take H to be much bigger than 1. And from the expansion, we have been able to read what was the first leading order, which is AFS, and Hernandez-Lopez. And if we replace inside our even dressing factor now this particular ratio, what we generated from our dressing phases, we have a solution which is compatible with crossing. We generate exactly this ratio of few terms. This, in principle, completes the proof of crossing. Of course, is not enough. Once you have some phase which solve the crossing equation, you can still have freedom to add the CDD factor, what are called CDD factors, so some function which satisfy homogeneous crossing equations and does not modify the solution. So we still need to check that all the other properties are satisfied. So now I come to the final part of the talk, which is indeed regarding the check and possible future directions. So what we have are analytic expression for this mixed fluxes matrix which satisfy the symmetry requirement. And one property, for example, that we check is that this function has good periodicity properties for the different values of M. If you look at what is the dispersion relation of a right particle with arbitrary bound state number M, is this solution here. And you can see that as a certain periodicity. If you shift M by K and the momentum by minus 2 pi, you obtain the same type of dispersion relation. And this would be nice if also this metric has some nice periodicity exactly in the same form of this dispersion relation. And this is what happens, actually. So if you shift the bound state number by K, is equivalent to shift the momentum by minus 2 pi. And somehow this as matrix, you don't have to study all the region of all momenta and all the bound state number, but it's just reasonable if you restrict to some bound state between, for example, 1 and K, because all the other bound states correspond to shifting this momentum here, okay? No, this is something, what we did was to check, for example, parity and Char conjugation and parity. This is not something we should expect, but it would be nice if there is either a symmetry like this or some monodromy of the solution. So this is something, in principle, doesn't have to hold, at least for me. But if you have all the possible, and what happens? In Ramon cases, you restrict momentum between 0 and 2 pi, and you have all the bound state number. Normally, what happens is this. Here, you have all the momenta and all the M's. But it would be nice if you can restrict still between 0 and 2 pi, and consider all the bound state number, or consider all the momenta, but restrict the bound state number between, say, 1 and K minus 1. So, and clearly, there must be something which reduces your space of possible parameters to a subset. Otherwise, it seems to be too much. And another limit that we consider, still 5 minutes, or a bit more, okay. Another limit that we considered was a paper in 2023, and a similar one came out before. Actually, a similar limit was considered by Fontanella and collaborator, is to study the energy as a function of the momentum, but instead of looking to all possible region of momenta, just to take h to be very small, and if h becomes very small, basically you have a singular as only one minimum, so this dispersion relation becomes something like, say, an angle. And you look around this minimum of this dispersion relation of fluctuation of order h. And if you do so, the theory becomes relativistic. And in particular, the spectrum of this theory contains a finite number of particles with masses which goes from 1 to k minus 1. And this is very similar to what are called a fine Toda theory of type A. Anyway, so there is a spectrum which is much restricted. And if you apply the bootstrap in this particular relativistic limit, what you obtain is that the relativistic S matrix contains some CDD factor and something which is the minimal solution to the crossing equation, where these are the same function I was introducing before. But before the limit, the solution is quite different, our proposal, because we have something which is u plus 2I over h and u minus 2I over h, which in the relativistic limit becomes some rational function of the rapidity, while by solving the bootstrap in the relativistic limit, we obtain some hyperbolic function of the rapidity. So the question is how this proposal can reproduce exactly this relativistic limit, and it does in a very non-trivial way. So what happens is that exactly this term reduces to a ratio of rapidities, but this even dressing factor produces exactly the inverse of this ratio of rapidity and also produces this ratio of Sinch. So this is quite nice result, I think, which I think is a good indication of the correctness of the proposal. So other thing we tested was a large tension limit, so what is called near BMN limit of the proposal, and we agree that 3-level matches perturbative computation at one loop in matches the cut constructable part of the S matrix, which can be found, for example, in the paper by Lorenzo Bianchi and Ben Hoare, but many other papers have been published, for example, by Linus Wolf and Arkady Young also. So it's still a mystery why we don't have a match for the non-cut constructable part. I think some of this computation would be interesting to review, but this is something which also in the Pura-Moramon case, there is no agreement as far as we know, and also from the proposal of the quantum spectral curve, there is no agreement about this part. And then the massless S matrix should correspond to a particular limit of a massive one, in which u plus and u minus, your Zukowski variable, are very close to the cut. And in particular, you can have that they approach the cut either this long cut on the right or the long cut on the left, and this should generate two different branches of your kinematic which are not connected by analytic continuation. This is the picture in the U-plane, and taking m to 0 in our solution for a massive, apart from adding little CDDs, we reproduce what should be the massless case, okay? So let me just go to the future direction. What we have now are equations for the thermodynamic Betanzas which involve all the dressing factors. These still need a lot to be investigated, so we still don't have a clear perspective of what are, for example, the integration region in which you should integrate the TBA equation. So we have the kernels, but still is a mystery if you have a non-unitary theory, what does correspond to integrate, for example, on the real momentum region or on the cut in the U-plane. What is the correct prescription is still a mystery. So the hope is that even if a contour can be ugly, you can deform them and choose some nice contour. As soon as you don't cross, for example, any poles, you should be fine. But you need to do this very carefully. So doing numeric in this model should be quite complicated. We hope to be able to do so at least in some region. For example, it would be very interesting the case in which k is equal to 1, and you expand the small fluctuation of order h, because that should correspond to the formation of the orbital point, the symmetric orbital point. But we hope to return to some of these questions in the future. And of course, there are more general integrable backgrounds. For example, you can substitute T4 with S3 S1, and that talk was given yesterday by Niccolò Primi. This is also something that you can do in the mixed flux case. Even Ramon is very complicated, so I don't know how much you want to push up, but it would be interesting to see. So I just put some of the direction that we retain interesting, and I finish here. So if there are questions at this point, I will be happy to.
Thank you. questions?
Thank you. So, can you explain what simplifies when h goes to 0? Like, because you expect massive simplification. Do you see? Because like branch points don't collide like in the case of n equals 4, h equals 0. So
when h goes to 0, what simplifies?
Yeah. Like, I mean, in n equals 4, there is always simplification. X become u, right? Everything, no cuts. Life is beautiful. So what about here?
Yes. Okay, I wrote down what should be the cut structure in this case. You have these two cuts and this cut. I didn't write down the expression of this point here. When h goes to 0, what happens is that these two cuts becomes like this. They overlap one each other. I don't know how much simplification you have. A thing that happens, for example, if you consider k equal to 1 from this formula here, is that basically there is some kind of identification of your particle of your model. Something like everything becomes massless, and every time you swap by, everything becomes massless because the massless mode m equals 0 and m equal k by this relation somehow are identified. So a particle of m equal k and m equal 0 are kind of very similar. If k is equal to 1, even the massive mode are equal to the massless one. So in this case, you can expect that there is something strange happening. I don't want to say nothing about the case in which h is 0 and it's true, it's a pure NSNS, so something nice should happen, but I think it's a strange limit from the point of view of S matrix because you have this long cut with overlap. And in this relativistic limit, it becomes some type of relativistic theory, but this is a particular relativistic limit in which also the momentum are expanded around some minimum. So don't know in general.
That's obviously very interesting to us with the BS phase. So what does it really do? If you think of some kind of small g expansion of the thing, so you cancel some terms, and was it like a discontinuity? I mean, what's
sorry, I didn't understand the question.
If I take your new phases,
yes,
and do a small g expansion, so what would I see as a difference to BS?
Small g expansion? What do you mean? Sorry.
Yeah, small h, shall we say?
Okay, small h expansion of a phase. I think it's the question of Collier.
Right.
So I still don't know. I should try. But I mean, apart from this relativistic limit is similar to do that, right? Because you have that, I mean, h is small, but I'm also expanding like a small momentum around my solution. And in this case, the theory becomes relativistic theory composed of massive particles. The question if you also go away from this point is something which should be investigated. For example, I know Alessandro Sondini, together with Andrea Day, did a proposal for the pure NSNS case in which they proposed some S matrix which now I think they consider to be one in the same collinear, in the case in which the momentum were collinear, and they managed to reproduce the same spectrum of this Verzomino-Witten model. But that is not a smooth limit, so who be interested to revisit this limit having the correct S matrix? Because it's strange that that limit is not completely smooth, so it's still curious how they managed to reproduce the spectrum. And we expect to reproduce the spectrum as a limit of a total S matrix, I think.
Okay, thanks.
I don't see any more questions. Maybe I would ask a question. Some people raised this question, including me. What would be a fishnet type limit here in this model? You don't have any idea?
No, I don't have any idea.
Let me maybe give some hint. If you can show me...
yes.
if you can show me the dispersion relation, like with...
Yeah, let me see. Okay, this is for right particle and for left here.
Yes, this one. So in our paper with Omer and João Caetano, we observed actually this limit already on this level. Like you send h to 0, p to I infinity, and then instead of this first term, we had 1, and then it nicely scales into some some dispersion relation with twist, yes, like spin chain with twist. Here, it's natural to maybe to send, if it's not crazy, it doesn't look crazy to you, m to I infinity, p to I infinity, yes, and then you can balance two terms. And I think in our case, the S matrix truncated to something like the homologic of ON. So maybe it could be done
okay.
this way here.
We can discuss it.
Interesting to see.
Yeah.
Okay,
Thank you.
If there are no more questions or proposals, let's thank the speaker again. I don't know.
Yeah, let's see. Hello, hello, can you hear me?
Yeah.
Okay. Yeah, I didn't need to point at that. Yeah, that's right. Okay, good. Thanks.
Good.
Yeah, perfect. Okay, so how do I? Okay, great.
So let's pass to the next talk. Bogdan will tell us about massless modes and the ADS3 CFT2 quantum spectral curve.
Hey, thank you, and thank you for the invitation. It's an honor to speak to famous physicists like Nadav at famous institutions, you know, like this institution. So it's a great pleasure. But I'm just trying to continue the theme of yesterday's format. So I'm going to. Oh, hold on. Give me a chance. So this is based on some work that Simon Ekhammar, Kolja, and I did in this paper, and also in ongoing work that the three of us, together with Charles Stool, who is my postdoc, he's sitting in the front row here, have been doing. And I just want to emphasize that besides this old person and this slightly younger but still old person, there are two really excellent younger people who've done a lot of brilliant work, and I want to stress that you should be really thinking about them when you're thinking about this talk, and of course my old but young collaborator. So I guess we had a very nice talk by Davide, who introduced a bunch of these things. But coming from a string theory background, I just want to frame this in a slightly bigger picture, because I feel sometimes some of the string theory detail gets a little bit lost. So actually ADS3 as 3T4, what we mean by that is a near horizon limit in the Maldacena sense of a bunch of D1s, D5s, F1s, and NS5s, right? So the D5s and NS5s in general are parallel, and the D1s and F1s are parallel and sitting inside the 5 branes. And so really there's a lot of different charges that we can pick, right? So it's not like D3 branes, ADS5, where we pick one integer. Here we're really picking 4 integers. And even this is a slight oversimplification because there are T-dual pictures, but I'm not going to get into that. So if you compactified type 2 string theory just on T4 in flat space, you would have 25 moduli on this T4 that you could change, and it would, they're all moduli, so you could change them freely. But because you've got a curved geometry, 5 of those moduli get removed. Okay? So instead of just having what we're used to in ADS5, having this lambda parameter that we can tune, here there are 20 parameters that we can tune, and these 20 parameters are different depending on which charges you pick. Okay? So what we tend to think of in the integrable setting is that we have 2 parameters, one which controls the number of Neves-Schwarz 5 branes, and the second parameter, which controls the number of D5 branes. And the number of D1s and fundamental strings has something to do with the volume of T4, depending on exactly which charges you choose. But the volume of T4 never features in our discussions to date. And so somehow it's only really these two integers, the number of D5s and Neves-Schwarz 5 branes, that are important. Okay. Yeah, so feel free to interrupt me, obviously, if you have questions or saying something that's not clear. And this case, as we heard in the previous talk, where K is non-zero but H is 0, should give this very beautiful Maldacena-Oguri WZW model whose spectrum is completely known. On the other hand, going away from this point in the Maldacena-Oguri language, in the RNS formalism, is essentially impossible or very, very challenging, right? You can turn on a little bit of Ramon-Ramon flux, but turning on a lot of it is, you have to calculate order by order, insert more and more vertex operators for this H deformation, and so it becomes very hard. On the other hand, the K equals 0 case, which is what I'm going to talk about in most of this talk, is, well, not really connected to this Maldacena-Oguri point, and it's only integrable methods that you can use to calculate anything. Okay. So this slide I'm going to skip, and you can ask me about it afterwards. It's about the CFT2 side of the correspondence, and all of this is to say that we know extremely little about it. So ask me later. So now I'm going to get into sort of slightly more familiar territory. What I want to do is I just want to introduce these ideas that probably a lot of you know very well, but just in the context of ADS3. So you take, let's first talk about the S matrix of this background. So you take a gauge-fixed Green-Schwarz action. This is my attempt at schematically drawing a magnon scattering with another magnon, and notice that the world sheet is infinitely long. And when you do the scattering, you can figure out that there's an exact dispersion relation that in the mixed flux case was first proposed by these guys, and then we generalized by us to massless modes. But the S matrix that you obtain, the two-body S matrix that you obtain in this process fixed by symmetries, satisfies the Young-Baxter equation and can be most nicely written in terms of the Zhukovsky variables. So I'm very happy that Davide introduced these variables in the last lecture, so I can go, in the last talk rather, so I can go a little bit faster. And for the most part of my talk, I'm going to be setting K equal to 0. Remember, I'm going to be in the pure Ramon-Ramon case. So there isn't really a distinction between left and right moving particles. But what's new compared to ADS5 is that there are these massless modes. So in ADS5, we not only have K equal to 0, but we always have M equal to 1. But here we can also have mass equal to 0. And OK, I don't really want you to absorb all the information on this of these terrible beta equations, or huge beta equations or beautiful beta equations, depending on where you are on them. But these beta equations have got a bunch of roots, some of which are auxiliary roots, some of which are momentum-carrying massive roots, but there are also these massless roots, right? So from n equals 4 or ADS5, you'd be familiar with these roots. This would be like a subset of all the roots that you have in ADS5, but there are these additional massless roots. And the beta equations, the only thing I really want you to take from this long expression is that they have a bunch of rational terms in terms of the Zhukovsky variables, but they also have these dressing phases, very much like what was introduced in the last talk. So here is a dressing phase for the scattering of two identical massive particles. Here is a scattering of a left massive particle with a right massive particle. And here is a dressing phase, for example, of a massive and massless particle. So the circle, as opposed to bullet, is meant to be massless as opposed to massive. OK. And similarly, in the massless beta equation, there is a dressing phase just involving the massless particles. and one involving the massless and massive ones. Okay, so this form of the equations is fixed by this symmetry argument, and the dressing phases satisfy certain crossing equations that have been known for a while. But what happens is, if you try solving this beta ansatz, you're really getting the spectrum of the theory as the world sheet is very large, as L goes to infinity. And in ADS5 and ADS4, this is not a problem, because, or at least it's a sort of very valid approximation, because wrapping effects, so going around the world sheet, are suppressed exponentially with the mass. In ADS3, we have massless states, and the mass can be 0, so this exponential suppression goes away. And so that was a point of view that Aniceto and Abbott emphasized. I should have included their papers here, that emphasizes some potential challenge to the asymptotic beta ansatz in ADS3. So we were able to, back in the day with Alessandro Torielli and Diego Bombardelli, we were able to come up with a massless sector TBA, which seemed to overcome these problems. But actually, looking more closely, it turns out it's the interaction between the massive and the massless states that is yet another challenge on top of that. So I think the more modern methods of the quantum spectral curve, of the TBA, allow you a way of incorporating these wrapping effects, these massless wrapping effects, and not, you know, place the asymptotic beta ansatz in a much sort of firmer footing, and tell you about in what limit it is valid. And what seems to be quite nice about the quantum spectral curve is that the internal kind of bootstrapping consistency of it places even stronger restrictions, as I'll try to show you in a bit. It places even stronger restrictions on these dressing factors. And so there are some little subtleties that we were able to fix by looking at the self-consistency of the quantum spectral curve. Okay, so I guess maybe 2 years ago now, these two papers of Andrea Cavaglia, Collia, Alessandro Torielli, and I, and a paper by Simon and Dima came out at the same time, in which we looked at the Q system of PSU 112 squared, which is the symmetry of these ADS3 backgrounds. And the Q operators should be roughly familiar to you if you're familiar with the n=4 theory. There's just a bit fewer of them. And amongst them are sort of some preferred operators, which are called QK, and some other ones which are called PA, and K and A both run over 1 and 2. They're in the fundamentals of the non-compact and compact SU2s. And there are these QQ relations. So this is for one copy of PSU 112, and then there's a second copy. So let's say this is the left one, and then there's a right one where you put dots everywhere. So for example, amongst these relations, here is a Q, here is a P, there is a particular relation between the Q's and the P's and the Q's A/K's. And there's lots of these relations, and the consistency of these relations is what's important to be able to construct the quantum spectral curve explicitly, and these plus minuses are, of course, the famous shifts in the Zhukovsky variables by plus or minus 1. Okay. But that's not everything. You still have to tell me what is the analytic structure, right? So these Q functions have a certain analytic structure, and it's always assumed in these games that the P's have a single shortcut that goes between minus 2h and 2h, where h is the coupling constant, and that what this implies from the QQ relations is that the Q's themselves have got either cuts, an infinite tower of cuts below the real line, that's these guys, or an infinite set of cuts above the real line. And so there are these two solutions because the QQ relations are essentially, that part of the QQ relations is a second order difference equation, so you get two linearly independent solutions. So what should you do with them? Well, actually in the Gong-Show we heard something similar already. There's a gluing condition, right? Which tells you that the Qs with cuts in the lower half plane are related, the left Qs are related to the right Qs with cuts in the upper half plane through this constant matrix G if you go around and through the cut, through this cut of the P function. So this is gamma, and this is gamma bar, what we're going to call like this. And one is, of course, the inverse of the other. And the matrix G, the gluing matrix, turns out that you can take to be in this form off diagonal with some constant alpha. Okay. And once you have these relations, it's often also very useful, just like in the ADS5 case, to introduce the Q omega and the P mu systems, where essentially you relate what happens to Q under the deformation gamma to Q dot guy through this function omega. And so these gluing conditions, together with the QQ relations, allow you to determine that there's some operator omega, which takes this form here. Similarly, there is a P mu system, and P under now gamma bar, so remember gamma bar is going in the opposite direction to gamma, is related to P dot operator with this with these mu's, and these mu's again through the gluing conditions here and the Q relations here. If you work a bit, you can find out that the mu's look like this. There's a question? We good? Okay, so if you want, that's kind of the construction of the quantum spectral curve, but one really nice feature is that it's possible to take a limit of these operators where you declare that some components are large, and as a result of the QQ relations, others are small, and you study the quantum spectral curve in this limit. And in the limit, you can recover the beta ansatz equations, the ABA equations. So in these papers, it was proposed that you take omega 1, 2 dot and 1.2 large based on experience with n equals 4 quantum spectral curve. And as I'll sort of review shortly, if you do that, and kind of apply the ADS5 methods, you will recover the massive beta equations. So just the subsector involving only the massive roots. But more recently, it's been proposed that there are some the massless modes. So that was following these papers. There was this puzzle, right? What happens to the massless modes? The massless beta equations should somehow be encoded, and what we did more recently with Simon and Kolya is we proposed that there are zeros of the mu functions which will correspond to the massless modes. And this was very much motivated by earlier work by Simon, Kolya, and Nikolay Preti, who looked at as a kind of more complicated subsector of n equals 4 theory where you take non-integer spins. So this is in a much more sort of complicated setting. And they found that there were massless modes and zeros of these functions that appear there too. But here, these zero modes already appear in just the perturbative closed string spectrum, rather than in some more complicated analytic continuation. Okay. So, like I said, we specify that these guys are going to be large, and then we just apply the QQ relations. Okay? And this is, I'm obviously summarizing here a lot of computational detail, but these QQ relations, together with saying that some things are large, really restrict what the P's and Q's can look like. and some part of the ones that remain. So these are the ones that remain. And some part of it is kind of, let's say, simple looking. So it's kind of rational looking. So you see you have these B's and these R's. They're all rational functions. And also, you get these new massless roots appearing here, and they also appear essentially rationally, okay, with a square root, but essentially rationally in the definition of the P's and Q's. But in addition, there are some factors which are undetermined, which will contain the dressing phases. Okay? And it's this part that's kind of most interesting, because when you plug those in, the gluing condition that I told you about imposes what look like discontinuity equations for these different dressing factors. Okay, so you can obviously, I can't show you all the details of all these expressions, but you get some discontinuity equations for each one of these for each one of these, well, they're not really dressing factors, these scalar factors. They're sort of like half of a dressing phase. And these discontinuity equations are very explicit, and so it's possible just to solve them. You know that there is some cut. When you cross the discontinuity, you've got to get a bunch of stuff like this. And don't worry about the fact that I've got proportionality constants here. We actually know how to solve this with an equal sign too. I'm just being quicker here, suppressing some technical details. Okay, so let's take one example. Let's look at this particular scalar factor, which, as you can see, has something to do with massless modes. And let's try to solve this equation. And it turns out that the solution, well, for those of you that are now familiar with quantum spectral curve technology, these factors typically come as a product over all the, in this case, massless roots. And each one of these row circles takes this form. Thanks. So there's some scalar factor, which is some kind of rational factor, which is not very important. There is something that I've called theta relativistic, which, see here I have x and y, and here I have gamma 1, 2. And gamma 1, 2 are these beautiful variables that Andrea Fontanella and Alessandro Torielli introduced. And what's nice is that this factor here, it takes a difference form. And the explicit expression for this, somewhat surprisingly, is, well, up to this sort of minus sign, if you want, is exactly the same as the dressing factor of the Zamolodchikovs in Sine-Gordon soliton anti-soliton S matrix, like the very first integrable paper on this subject. So you can see that basically this row wants to be this Zamolodchikov dressing factor. But there's some slightly annoying constant phase that seems to come up. Okay, and I'm going to talk a little bit more about that now. Okay, so how do we get the massive beta equations? Well, this is a kind of well-trodden path by now, similarly to ADS5. You take certain combinations of the Q functions, you evaluate them at the zeros of certain functions, and plug in these large volume limit expressions. Whoops, I'm going the wrong way, aren't I? So you plug in these sorts of expressions and similar ones for the Q slashes, and you recover the beta equations that I showed you at the beginning. And you recover them only as long as you identify these scalar factors from the quantum spectral curve with the dressing factors of the S matrix in this way. So you have to make these three identifications for massive left-left, massive left-right, and mixed mass scalar factors. And you see here there are already 6 equations. So actually there's a lot of consistency condition that comes in. Each one of these equations looks slightly different. You only get 3 choices. You got to match to 6 equations. So it's non-trivial that this works out. What about the massless beta equations? So this was the kind of new contribution of the more recent paper. If you look at this combination of the P functions now, and you evaluate them just above and just below the massless cut, then you reproduce, so again, I'm not showing it, but you reproduce the massless Bethe equation up to some strange phase, which I'm going to keep drawing now in light blue. And this strange constant phase, I think, deserves to be understood a little bit better. It sort of has the feeling of like a twisting just of the massless sector, something like that. And again, the matching works as long as you identify the S matrix dressing factor in this way, the massless one, and the massive one in this way. Okay, so that's nice. But what's even nicer is that if you calculate in the quantum spectral curve, we can understand crossing as a combination of doing this gamma bar contour and, as a combination of a gamma bar contour shifted one down and one up. So I think this is this kind of familiar to everyone who's looked at crossing in ADS5. The crossing transformation involves crossing both x plus and x minus. And in the massless case, as was shown by Sergey and Alessandro, crossing, in fact, is gamma that I introduced earlier rather than gamma bar. Okay? And so since we know the solutions, right, and since we know what discontinuity equations these guys have to satisfy from the gluing conditions of the quantum spectral curve, we can plug them in to our expressions for, for example, here, the dressing factor is this particular combination of the quantum spectral curve scalar factors. So you can plug in and work out what are the crossing equations for all these guys, for all the dressing factors made up of these combinations of the scalar factors in the quantum spectral curve. And at first we were very excited. It was really nice because all the crossing equations come out exactly the same as in the S matrix. So that was a nice consistency check. And then if you look at the explicit solutions, so not just the crossing equations, if you look at the explicit solutions, they lead to the same dressing factors that we heard about earlier today, but just with k equal to 0, for the massive and mixed mass cases. But there was a funny disagreement between the quantum spectral curve massless dressing factor and the one that seemed to come out from the S matrix. So if you remember, I showed you one quantum spectral curve's scalar factor, which was related to the Zamolodchikov S matrix. There's also this other factor from the massless BES phase. So this kind of looks nice, but then there's a weird factor of minus I, which is related to this e to the minus 3 pi I over 4 that I showed you. And this disagreed, and so this expression disagreed with the S matrix result of, I guess, Alessandro and Sergey, where they, instead of this minus I, they had a factor like this. Now, what's also funny is that if you take this scalar factor, this dressing factor, and you ask, is it unitary? It doesn't look unitary. So then you've got this tension, right? This scalar factor solves what we think is the right crossing equation, but doesn't look unitary. Weird, right? Maybe, instead, what we should do is, we should change this guy by a factor of I, so that we have unitarity, but then the price we end up paying is that it'll solve a different crossing equation. It'll solve a crossing equation with an extra minus sign on the right-hand side. So from the point of view of the quantum spectral curve, that's not a problem, right? Unitarity seems much more important than some arbitrary crossing equation. And we are allowed to do this change by I. It doesn't mess up the identification with the Bethe ansatz equations, because there is this funny blue constant phase floating around, and that phase allows you to reabsorb these factors of I. So the conclusion that we were drawn to, oh, sorry, let me just say why, maybe, do I have like 3 minutes? 2.5, wow, strict. Just 1 sec. So I guess that's one possibility, right? That you redefine by I, but then maybe we should match to Alessandro and Sergei's answer here. How could we do that? Well, one way we could do that is we could take our solution of the discontinuity equation and multiply it by some extra factor so that it gives you the right, so that it reproduces this term in the dressing factor when you put everything together. But this actually introduces a much bigger problem. Because what happens is the dressing factor for massive massless scattering will then change dramatically by a term like that includes this, so it's some non-trivial function. But on the other hand, the dressing factor for massless massive scattering remains unchanged. And these two guys are related by unitarity. So now you really mess up unitarity badly if you introduce this extra factor, right? So this felt to us to be not quite the right solution, and so we preferred to instead put a factor of I here. And I think recently, correct me if I'm wrong, you guys have kind of looked at massless crossing again, and in the S-matrix formalism, and it looks like, am I right in thinking that maybe there is an extra minus sign hiding there somewhere? Yes. Okay, so. Okay. Yeah, so maybe we discuss a bit more, but what I'm trying to say is that there seems to be a nice thing happening now fitting. So from the quantum spectral curve, it's sort of much nicer not to have this factor of minus I, because then really the massless dressing phase is really the Zamolodchik of 1, and that seems to fit with the latest analysis. Okay, so let me finish on some work that, that's perfect, that Charles, who joined our collaboration, and Simon and Kolya and I have been doing, but really a lot of heavy programming by the impressive junior collaborators here, so I want to just emphasize how challenging, these slides are going to make this look simple, but it's unbelievably impressive what those guys have been able to do. And so we tried to find some new solutions to the quantum spectral curve, generalizing these massive solutions here. But this is very hard because of the log cuts that are present. It turns out that if you consider as kind of symmetrical sector where the left and right P's and Q's are equal to each other, which in particular implies this for the spin and off-diagonal component of angular momentum, you can find solutions, exact solutions to the quantum spectral curve, which have just massless excitations. So this is the angular momentum, and we will be setting K0 to 2, and we will be setting L to 2 or 4, and then you will get the anomalous dimensions. And I just want to caution you, everything on this slide is still work in progress, so the numbers may change, but I think we're quite confident of the general structure. So here is the L equals 2 anomalous dimensions in the dots, the numerics, and I guess the analytics, right? And here is the, I'm sorry, this is the curve I should have been pointing. The solids is the numerics and analytics at weak to strong coupling. And for L equals 4, this is the curve. And as you can see, asymptotically, they tend to these very nice Regge trajectories that we've been hearing about in this conference. And it's also possible to find the analytical solution in the case of L equal to 2, so these very short operators just with 2 massless excitations. And okay, again, caution, but the general structure seems to be a 1-loop correction, and then I guess not the next order, but the 2 orders after that correction and something at 6 order. Okay, so let me conclude. The ADS3 CFT2 quantum spectral curve in the Ramon-Ramon case, well, it passes all these nice consistency checks and in matching to the ABA, and in particular, it seems that the original proposals were already kind of good enough. They knew about the massless modes, even though we didn't know about them back then. And we seem to get some nice sort of tying up loose ends results about the crossing and dressing factors. And in particular, it seems like there shouldn't be anything here. That seems nicer, and the old Zamolodchikov dressing phase shows up. And I hope maybe in the near future we will have some more concrete results about the numerics. Okay, so let me stop here. Thank you. Sorry, I overran a bit.
Questions? Joe?
Sorry, in your last slide, what is G?
I guess it's H.
So it's 8. It's
Yeah, it's H. So the yeah.
And there is no field theory to check it, yes?
There is no field theory to check it. Yeah. So, sorry, what?
That's what I'm asking. There's no field theory to check it.
Yeah. So, but what do you want me to do, right? Ask Juan. So there are some words, right?
So in a sense, it's alpha prime. It's square root of alpha prime.
Yeah. Well, but that's at strong coupling. No. So, right, that's at strong. No. So this is done in the quantum spectral curve at small values of H. What's the dual field theory? I don't know. Well, I can. Here's my slide, words. Who knows? Is the summary we can, we've talked about this before, right? It's something to do with a deformation of symmetric NT4. There will be some point in the moduli space of that thing which should match. How you calculate at that point, I don't know. There is a nice Higgs branch story which might be related to this that I talked about 10 years ago at this conference in London. But it's, yeah.
I also have a question about this sign, which is not very clear to me. The reason why we revisited the crossing equation because the point is that this A of gamma factor in the mixed flux, we couldn't generalize in such a way that satisfy all the properties. In particular, there is an SU2 symmetry between the two massless modes.
Yeah.
And we didn't manage. So we revisited crossing, and our approach was more Lasciota, Copetti, and Korov. In this case, what I don't understand is that you have some quantum spectral curve. You derive a crossing equation from a quantum spectral curve with a, do you have some freedom in choosing the sign from your QSC or
no?
So in principle, you should have this I factor or
so, yeah,
it's not completely clear to me this.
So because we have, well, look, in the massless case.
Maybe we can.
You want to? Sorry.
we don't derive S metrics.
Yeah.
Derive the equations for the spectrum. We derive beta on that. And then it's up to you to identify what is dressing phase, what is not. That's just a name, right? Doesn't make sense.
And the gluing condition has no freedom in it. There isn't like some hidden minus sign.
Then it's just a freedom of notation, right? So you can, sigma, 0, 0, this combination or that combination. And then, of course, unitarity and crossing changes each time you change notations. That's it. But there is no freedom in the beta ansatz you get. Just a notation. Well, crossing equation is always is uniquely fixed. What is not fixed is left-hand side because you can change notation of what you call the dressing phase. Because obviously you can reabsorb different factors and beta ansatz and say, maybe that's dressing phase or that, right? The same thing as you're doing, right? In different papers you call different factors absorbed into sigma or not. That's the only freedom because there's no objective way of defining what crossing phase is. This is a quite ambiguous notion itself.
I guess.
Normally in massless mode, you have different branches of kinematics, left, right, depends on. Is an assumption what you verify that there is a single dressing factor to the massless? Is an starting assumption, or is something you can derive? Because from the bootstrap, as matrix bootstraps, people assume that there are different, there is a single analytic function for the dressing factor, which is the same for all chiralities, but
I'm not sure that there are genuinely different massless. I think this a little bit is like to do with. I'm happier to go to the 2 pi limit rather than to the 0 limit, and so then it's, there are those two things are connected, right? As I analytically continue. Yeah.
So on the last slide, the analytic data is at weak or strong coupling, because it's like in the right side of the
sorry, it's at both. So there is numerics at weak coupling, and then there is an extrapolation like this to stronger coupling.
Okay, and an analytic prediction at weak coupling.
And in this particular case, there is an analytic. Yeah, I think for L equals 4, it's hard. It seems to get an analytic expression.
And another fast question. So is there any confirmation of the predictions of quantum spectral curve, any matching with the actual string theory data, with classical solution or with anything?
So we were looking really at the massless guys, so those are very hard to understand.
Okay, in this case, right, but in general for ADS3, I mean, we don't know how to compare with field theory. Can we compare something?
Did you guys compare in your earlier work on the massive case? I think the trouble seems to be these one-loop corrections, right? That they are quite problematic. They're the ones that you know well about.
Hi, Bogdan. Hey. So if you set h to 0 in your very impressive beta equations, asymptotic ones, do you get something that looks like a spin chain or a quantum field theory?
I mean, at weak coupling, you are asking. So not really to 0, you mean the first order guy?
Well, in n equals 4, you can set...
Yeah, okay, in the same sense that you mean, yeah. So for the massive ones, you get these spin chains that are, well, they are essentially a projection down of the n equals 4 spin chain, right? And for the massless ones, I don't think there is going to be a spin chain as such. I think our conclusion, Ale, was that it's like some kind of field theory, and it would be nice to understand this field theory a bit better, and it was starting to look like a n equals 2 sine Gordon, but not quite. And these dressing factors that I was showing you, these Zamolodchikov dressing factors, they kind of have that feel. So, if I'm just going to start dreaming now, as opposed to, thinking rationally, I would like to have a spin chain that interacts with like a sine Gordon field theory somehow, and that's what's at weak coupling.
That short comment. So in n equals 4, you can also get non-trivial spin chains like that at 0 coupling, but if you start from non-local operators like BFKL, you get exactly similar massless modes, and those dressing phases are quite similar. So it looks like it's a field theory, but operators being kind of a bit non-local. Maybe you can model it this way.
Thank you.
Okay.
If you could put it a bit closer to the center.
Yeah, I will try.
Just in case you move your head.
Yes. Okay.
So a couple of announcements. So people who wants to appear, wants to be added retrospectively to the conference picture, there will be a special green screen photo session in the beginning of the lunch break. So then, if you got some cool pictures you want to share with everyone, be sensitive. Please send them to IGST 2025 announcements@gmail.com. You can find address on the web page. Right, and then for the conference dinner, obviously that's all the stocks are building up to this event. We'll start walking at 5 from the coffee break place at 5. So let's accumulate there.
Let's start the next talks. The next talk will be of Charlotte Christiansen, 1/2 BPS NAM-pole defects in N=4 superrank mills. Please, Charlotte.
Okay, thank you very much. So first of all, I would like to thank the organizers for setting up this interesting conference in swinging London and inviting me to speak here. Let me say that I'm especially happy about all the Gong-Show talks and the poster session. I think it was a great idea to include more of those. So what I will be speaking about is 1/2 BPS NAM-pole defects in N=4 super young mills. And the talk is based mainly on a paper I wrote with Adam Shalabi and Deliang Zhong, but also some papers that I wrote with Costa Serembo. And there will also appear some earlier work by Marius Deleuve, Thomas Gomber, and Georgina Dopoulos. Okay. So what I will do is to start by giving a review of 1/2 NAM-pole defects in N=4 super young mill theory, focusing, of course, on their integrability properties. And here I will pay special attention to the so-called Bruker-Witten surface defects, which have only very recently begun to be studied from the integrability perspective. And the reason why I chose to look at 1/2 BPS NAM-pole defects is that being supersymmetric, they can also be treated by supersymmetric localization, and by using supersymmetric localization, you can get exact results for instance, one-point functions in the background of the defect, and these one-point functions, they reveal some intriguing, interesting structures of perturbation theory. And that is the content of these 2 points here, and then I will finish by a summary and an outlook. Okay, so NAM-pole defects in N=4 super young mills, they are hyperplanes, which are characterized by some of the fields of the field theory diverging as you approach the plane. So more precisely, the fields have to diverge as 1/r, where r is the distance to the defect. And these NAM-pole defects, well, they're characterized by some classical fields. And these classical fields, of course, they have, by definition, to satisfy the classical equation of motion of my field theory. But I will also demand that they solve the NAM equations, which is what makes the setup supersymmetric. And as far as I know, there exist 3 types of such defects in N=4 super young mills, corresponding to the 3 possible values of the codimension. So there's the domain wall defect, which is of codimension 1, is characterized by 3 of the scalar fields having a vacuum expectation value different from 0. And let me remind you that this scaling is necessary in order for the defect CFT to be possible to be, for the theory to be possible to be a defect CFT. Okay, the domain wall defect is characterized by 3 of the scalar fields having a non-vanishing vacuum expectation value, and that theory is the one which has been studied the most. Then we have the so-called Gukov-Witten surface defects. They are, as indicated by the name, they are surface defects of codimension 2, and they are characterized by 2 of the real scalars having a non-vanishing vacuum expectation value, and also some gauge field potential components having non-vanishing waves. Finally, there's the Hoof loop line case, where we insert a monopole in n equals 4 super Young Mills, and then the world line of the monopoles becomes a one-dimensional defect. And to create a monopole, you need 3 components of the gauge field potentials of a non-vanishing wave. And in order to make it supersymmetric, you also need that one of the scalar fields has a non-vanishing wave. Well, I'm looking at a scalar field. Yeah, okay, yeah, in 4 dimensions, no. Yeah. Good. So here I have summarized some of the properties of these NARM pole defects. So when you introduce a defect in n equals 4 super Young Mills, you typically also introduce some extra parameters to describe the theory. So here again, the domain wall, the Gukov-Witten surface defect, and the Hoof line. So these parameters, they can either be discrete or continuous. So for the domain wall, the extra parameter that one introduces is discrete. It's the size of some SU2 representation in the field theory language, or some background magnetic flux in the string theory language. In the case of the Hoof loop or line, the extra parameter is also discrete, and it's simply the monopole charge. The Gukov-Witten surface come in 2 different versions, known as non-rigid and rigid, and they have respectively continuous and discrete parameters. So all of these NARM pole defects, they have a dual description in terms of a probe brane system. So the domain wall is dual to a probe D5 brane. The Hoof line is dual to a probe D1 brane, and the Gukov-Witten surface defects are dual to probe D3 branes. And the geometry of these probes are of the same type, so they always have an ADS part, which lies inside the ADS5 of the background, and then a spherical part which lies into the S5 part of the background. And furthermore, the ADS5 part of the probe embedding shares some dimensions with the background ADS5, and that's what gives rise to the defect in the field theory. Now, these various defects, they have different symmetries. So the remaining global superconformal symmetry of the domain wall and the Hoof line is the same, but the Gukov-Witten surface defects have a different symmetry group. Also, there's a difference in the background fields, these classical webs. So, of course, they are in general matrices because the fields are on the adjoint representation of the gauge group. But for the domain wall, these matrices are non-commutative, whereas for instance, the Hoof loop, they are diagonal matrices. For the Gukov-Witten surfaces, they come in 2 versions again. One is commutative, and the other one is non-commutative. Okay. So let me say a bit more about these Gukov-Witten surface defects, which are less studied than the others. So, as I said, there are 2 real scalar fields which get non-vanishing waves, and also some components of the gauge field get non-vanishing waves. So in what was called the ordinary non-rigid case, then the waves look like this. So they are diagonal matrices. Now I combine the 2 real scalar into a complex scalar. So they are diagonal matrices with some complex numbers on the diagonal, and each complex number can be repeated a certain number of times. So these betas and gammas, they have to be real. And in this case, there's actually the space-time dependence appears out in front here, and it involves both a radial and an angular coordinate in the plane transverse to the defect. Okay, The classical background field for the gauge potential takes this form here, where the alphas are real and periodic. Okay, then there's also a variation of that, which is called the rigid case. And that's a case which occurs if you solve the classical equations of motion with an assumption of logarithmic scaling, and also the Nahm equations, of course. And in that case, the classical fields are bound to be non-commutative. And more precisely, they have to take this form here, where the T1, T2, and T3, they constitute some representation matrices of an irreducible SU2 representation. Can be any dimension a priori. So it's a little bit like the domain wall case. We have some SU2 representation appearing, but the similarity is deceptive. The setup has other symmetries, and there are only two scalar fields which get webs. So this logarithmic scaling also introduced some distance parameter R0. And the scaling as such is also not as you see normally in conformal field theory. But the original paper introducing these defects states that conformal invariance is recovered if you in some way do the path integral over this R0, and that this setup actually corresponds to setting beta and gamma to 0. So at the moment we are working on understanding this in more detail, but it does not really influence our study of the integrability properties of these defects. Okay. So let me say a bit more about the string theory description of these group of Witten surface defects. So here I start by writing down the metric of the 8s5 times s5 background with the 8s5 here and the metric on the 5 sphere here, which I parameterize in this way here. So in this coordinate system, the world volume coordinates of the probe D3 brane, which is dual to the surface defect, are x0, x1, r, and psi. And it's supplemented by some embedding functions. So the D3, it sits at a point theta on the 5 sphere, and then it also wraps an S1 on the 5 sphere, but that S1 is somehow linked with an S1 inside ADS3 via this relation here, where phi 0 is an integration constant. Furthermore, we have an embedding function for y, which is ADS radius. It is 0 at the boundary and grows when we go into the bulk of ADS. And from this, you see that the radius of this sphere that the D3 brane wraps inside ADS3, it grows as we move towards the interior of ADS. So the brane probe is somehow cone-shaped in ADS. Okay, and I don't know if it comes from supersymmetry, but the entire setup is supersymmetric. So at some level it probably does. Okay, but you see here there appears two integration constants, this kappa here and this phi 0 here. And they are both continuous, so there are, for the moment, no discrete parameters appearing here. And these two integration constants, phi 0 and kappa, they're related to the diagonal elements appearing in the classical webs for the scalars in this way here. So you see that what I denoted as a rigid case, which was supposed to be when beta and gamma go to 0, it corresponds to this integration constant kappa going to 0, which means that the size of the sphere inside ADS3 shrinks, naively it shrinks to a point, but the sphere on S5, it remains. Okay. So that is the string theory setup. Okay, so I will now finally let me get to why I speak about these objects at this conference. Namely, I want to look at the integrability properties at the one-point functions. So, of course, we know that one-point functions in the presence of a defect can be non-vanishing, and from conformal symmetry on the defect, they are bound to take this form here, where x perp is the perpendicular distance from the defect, if we consider a bulk operator. Of course, if this also requires that there's rotation invariance in the transverse directions, and if there's not, then there can also be some angular dependence on this C here. So in these setups that I've been talking about, we have these classical background fields, and due to these, the scalar operators built from scalar can of course have non-zero one-point functions already at tree level. And we find these one-point functions by taking our operator and plugging in the classical fields. So this is, in principle, a trivial procedure, but as we all here know, we first have to find our good conformal operators, and then we have to plug in the fields, and that is a non-trivial combinatorial problem. But sometimes it can be solved, and sometimes, at least at tree level and one loop, you can find the one-point functions in a closed form using the algebraic beta ansatz, and then we say that the system is integrable. And sometimes you can even go beyond the first few loop orders and derive an asymptotic formula for the one-point functions by using some kind of integrability bootstrap, which was done for the domain wall case by these two groups here. And now what we want to do is to see how far we can go with this program for these Hooker-Witten surface defects, which are less studied. Okay. Yeah, so here I have somehow just summarized the results. So what you do when you start studying a new type of defect, you typically start from some small subsector of operators and look if that is integrable, then you extend and see how far you can go. So we start by looking at the SU2 sector, which consists of just two complex scalars. And here, if you look at the non-rigid ordinary defect, then there are actually no one-point functions at all. But the rigid case, it's completely similar to the domain wall setup in the SU2 subsector, so you can read off the expression for the one-point functions at tree level from the result of the domain wall case. But that's somehow accidental, it's just in this small subsector. But it is integrable in that subsector for any size of this SU2 representation which appears. Okay, then you can move on to the SO6 sector, or the SL2 sector, which consists of one complex scalar acted upon by covariant derivatives. And what you find is that in the SO6 sector, you can write the overlap in a closed form for all values of these betas and gammas which appeared. And actually, that overlap is something which you can read off from an earlier overlap for a D3, D7 probe-brain system. But again, this is somewhat of an accident, but the formula is known from earlier works. Now, the rigid case where the SU2 representation matrices appear, it turns out to be less integrable than before. Actually, it's only integrable for the smallest dimension of the representation matrices for k equals 2. But then something interesting happens if you go to the L2 sector. It turns out that these non-rigid defects, they are actually not integrable. You cannot write one-point functions in a closed form. Whereas the rigid defects remain integrable, you can still find a closed overlap formula for the two-dimensional representations. And I should say that the way in which we test whether these sectors are integrable or not is by writing down the corresponding boundary state and acting on it with the odd charges of the integrable spin chain. And if that action of the odd charges on the boundary state vanishes, then there is a chance that the system can be integrable. And we go on and try to derive the overlap formula by using the strategy which has been devised by Gompa by using a KT relation, and then from solutions of that KT relation by some recursive strategy deriving the overlap formula. So by this method, we have derived some novel overlap formulas like this one here and here. These two were not known before. And let me just reveal what they look like. I should say that if you want to know more details, I hope you have looked at the poster by Adam, where he has, I believe, given more details about this. Here I just summarize the results. So here I show this new overlap formula for the SO6 sector for the rigid Hooker-Witten defect and for the smallest dimensional SU2 representation. So you see, it takes this characteristic form, which was also discussed yesterday by Shota. It involves a superdeterminant of the Godin matrix and then some ratio of Baxter polynomials. And there's only a non-zero overlap if the beta roots of the corresponding beta eigenstate or operator come in pairs with plus minus the same rapidity. And actually this overlap formula is of the achiral type, where the roots at the middle node have to be paired between themselves, whereas the roots on the outer nodes have to be paired with each other. So it's another type of overlap formula. But this was already predicted in these papers by Beinok and Gromov. Okay. And I should say that this case here, the rigid case for k equals 2, is of course the only case where we can dream of going beyond one loop order and find a completely integrable system. Okay, yeah, so what about higher loop integrability of these defect setups? Well, for the domain wall defect, we know that the corresponding string boundary conditions, they are integrable even when these VEFs or background magnetic fluxes are present. This is shown in some analysis by Kostya and George Linadopoulos. And in accordance with this, there has actually been derived an asymptotic all-loop formula for the one-point functions by these two groups. For the Guker-Witten surface defects, we know a bit less. The string boundary conditions are so far only known to be integrable without the presence of classical background fields. This is contained in the old paper by Degel and Ors. And from our analysis, we know that we can only have hope for higher loop integrability for the rigid case for k equals 2. Finally, for the 't Hooft loop, so far, the string boundary conditions have only been proven to be integrable without the presence of the VEFs. And there is a partial asymptotic all-loop formula derived also by Gromov and Beinok, but it's partial in the sense that the reflection phase has not completely been fixed. Okay. Yes, but what unifies, well, okay, these are, the status of integrability is a little bit different for the different defects, but maybe this just reflects that we've been working on them for a different amount of time. But what unifies them is that all of them are only known up to wrapping effects. So what could we do to try and learn about the wrapping effects? Well, we could try to see if we can learn something from localization, because as I said, all these defects are supersymmetric. So by supersymmetric localization, you can get some exact results for one-point functions of chiral primaries in the background of the defect. And such results actually exist for all three types of defects. So let me go through this in the case of the 't Hooft loop. So let's consider the 't Hooft loop and some chiral, the simplest possible chiral primary, and its one-point function in the background, it's a 't Hooft loop background. In that case, one can do supersymmetric localization for a Wilson loop, which is dual to the 't Hooft loop under S-duality, and then using S-duality, you can get a prediction for the one-point function in the presence of the 't Hooft loop. So the S-duality of n equals 4 super young mills, it exchanges lambda with size 16 pi squared n squared over lambda, and then it exchanges electric quantities with magnetic quantities and vice versa. But a chiral primary has no electric or magnetic properties, so it stays the same. Okay, so the expectation value of a chiral primary in the background of a fundamental Wilson loop is known exactly from localization. It was derived by Okayama and Simonov. So we can use this to get a prediction for the one-point function in the presence of a 't Hooft loop. So we apply the S-duality, or I should say these are Laguerre polynomials, and then we do an integral representation of these Laguerre polynomials and a large n saddle point for the resulting integral. And that leads to a planar perturbative prediction for the one-point function in the presence of the 't Hooft loop. And it takes this form here, where now R here is the distance from the operator insertion to the 't Hooft loop. So it's relatively simple, but becomes even more pretty if you uniformize it using Zukovsky variables this way here. Then if I strip off the space-time dependence, I'm left with this relation here. So x to the power L, and then 1 over x to the power of minus L. And when written in this way here, these terms seem to have different origin, and it's natural to interpret the first one as normal asymptotic contributions, and the last one as wrapping contributions. This is the same kind of split we have seen in other examples as well. And it becomes even, well, you can also see that this starts out as 1 over square root lambda to the power L, which is what we expect for such a one-point function when we take into account the normalization for field theory. And this one starts much later, a power lambda to the power L later, actually. But it becomes even more evident if you expand out the coefficients. So now I've expanded out the one-point functions with the space-time dependence stripped off. And the black terms here come from the first term in the equation I had, and the blue ones from the second term. So you see something funny happening. So all the, for all the odd operators of odd length, there appears to be no wrapping corrections. And okay, you also see that these blue terms here, they start out as at the order that you expect for wrapping corrections, namely order lambda to the power L when you take away the normalization constant. But the operators of odd length, they have no wrapping corrections. And the ones of even length have, and they start as expected at the order lambda to the 2L. It's also kind of interesting that not only do these odd coefficients not have any wrapping corrections, they also terminate at a low order for all length. And that's actually something you see also for the other domain wall setups. For the other defect setups. For the domain walls, you have exactly the same structure, except that all the odd coefficients here, they actually vanish. For Gucke-Witten defects, it's even more simple. You also have this truncation, but you have no wrapping corrections at all. Okay. So now it's actually easy to write down a formula for these non-wrapping corrections, the asymptotic parts, in a closed form. And it takes this, it looks like this. So there's a 1, and then there's a sum up to a power, which is the integer part of L over 2. Then we have this lambda over 4 pi squared, and then some combinatorial factor in front. And this formula here, we would like to recover from doing perturbation theory around the monopole background that is quantizing around that classical field that we had before. And that is actually possible. But let me, before going to that, say that we have exactly the same structure for the domain wall defect. It truncates at the same order. Okay, it vanishes for the odd cases, but for the even cases, it also truncates at a particular order. We have the same combinatorial factor and the same field theory factor, but then there are some Bernoulli polynomials coming up here, which depend on the size of the U2 representation matrices which appear. So now I'm cheating a little bit because I said I wanted to use this to understand the wrapping corrections, but actually I will postpone understanding the wrapping corrections until later. I'm, for the moment, trying to understand the asymptotic part. And let me do that for the 't Hooft loop case. So the very first term in this expansion here, we just get from inserting the classical web, that's easy. But to get any of the other ones, we have to quantize around the monopole. And that we have done. So let me tell you how you compute the one-point function in perturbation theory. So at the leading order, as I said, you insert the classical field, which is symbolized by these sticks here. And then the first non-trivial thing you can do is to make a one-weak contraction with one loop. And to do that, you need to find the propagators for the scalar fields. And it works in more or less the same way for all these defects, that there are some scalar fields which are easy and some which are difficult. The easy ones, they only mix with fields of the same type or same flavor, and there are some difficult ones which mix not only with other scalars but also with gauge fields. But you can perform the diagonalization process and find the propagators for the scalars. And in this case here, you need the propagator for two scalars of different type, one easy, one complex. And here I have written down what they look like. All the propagators in this monopole background, they are ADS2 times S2 propagators because of the symmetry of the problem. And the S2 part is taken care of by some Jacobi polynomial, and then there's some ADS2 propagator also. And here I've written down for the general value of the monopole charge before I set the monopole charge to the smallest possible value. And you see there's some relatively complicated sum over mode numbers, which comes from Kaluza-Klein reduction on the sphere. So this is a simple scalar, and this is a complicated one. But when you combine the two to take the full propagator, you have to subtract the two terms and some telescopes, and we're left only with two terms. And not only should we take the difference, we should also take the endpoints of the propagator to be identical. When we do that, something interesting happens. This tadpole diagram simplifies to 1 over 8 pi squared r squared. And then we have to also multiply by some vertex factor, which depends on lambda. And the final result is simply like this, where we have some part here which factors out in front of the one-point function as the space-time dependence, and then there's this simple coupling constant dependent factor. And using that, it's easy to see where this expression here comes from. This coupling constant dependent factor is simply the value of the tadpole diagram. And for a given L, this combinatorial number is actually just the number of ways you can make little n contractions on in an operator with L fields. So you put your L fields in a row, and then you have to pick out n places out of L minus n where you put a contraction. If you forbid contractions between the first and the last, and then there's another contribution if you contract the first field and the last field. So all these contributions, they come from simple tadpole contractions. These diagrams are simply flower diagrams with a varying number of leaves appearing. So that's pretty simple, and we see exactly the same phenomenon for the D3, D5 program system. There we had the same expression, but some Bernoulli polynomials. But those Bernoulli polynomials, they just come from tracing over SU2 representation matrices, so we can get the exact formula coming out again. And we see the same phenomenon for Gucker-Witten defects, similar structure, but as I said, there are no wrapping corrections in that case. Okay, so that's what we learned, and that leads me to my summary and outlook. So, summary, we have at least 3 examples of defect CFTs based on n equals 4, which are amenable to supersymmetric localizations, to integrability, and potentially also to boundary conformal bootstrap. The quantization is completed in all 3 cases. Supersymmetric localization has been completed in all 3 cases, and they have revealed an intriguing structure of perturbation theory. In the most studied example, we have actually obtained one-point functions from integrability up to wrapping interactions. So what we really need to do is now to understand these wrapping interactions, and we hope we have taken the first step in that direction with this work. And it leaves us also with trying to, I've said this many times, but I think one should also try to implement the boundary bootstrap program for these defects with non-vanishing classical fields. So, thank you.
Questions?
Thank you for the very nice talk. Since the localization result is also available for any value of the coupling, and yes, duality works as well, is it possible also to achieve a result for the strongly coupled situation for the TOF coupling, so expanding the localization result, a weak coupling, and get a strong coupling result for the TOF line? And in case, is it possible to check that we get to a correct result?
Yeah, I think, yes, you can also expand for strong coupling, and I believe we checked the first term there. You can probably check more if you work hard. Yeah.
Okay, thank you.
More questions? I wanted to ask you, what is known about generalizations for higher representations of the Wilson loop and maybe very high representations like
Yeah, that's interesting.
Giant or even huge?
That's a good question.
As duality provides some information.
In principle, these higher representations of the Wilson loops, I think they were only so far only derived from localization for the fundamental representation. But maybe if you work hard, you can get them also for higher dimensional representations and use S-duality to get some results for more general monopole configurations. It's an interesting problem, but yeah.
It looks like a complicated but solvable matrix.
Agree, yes.
So,
yes.
Okay, thank you.
Okay.
For this particular problem, why would you need it? We know the matrix model, so it's just for high enough representations. I'm not sure there are. Okay, good.
There's some special cases, I think, where the loop wraps many times, so some submanifold, but to have a very specific representation given by some...
Like big representation.
Yeah, big representation.
This is
would be interesting.
Completely trivial. Okay. If there are no more questions, let's thank again Charlotte. The next talk will be of Lawrence Eberhard, Rademacher, evolution of one-loop string amplitude. Please, Lawrence.
Thank you very much. Thanks very much to the organizer for organizing this wonderful conference. It's really nice that it's actually a conference about string theory and you don't have to shy back to say technical details and so on, so I really enjoy it. This talk is not about integrability in the traditional sense, but it's about computing integrals in string theory. So in that sense, we're still doing integrability. And it's based on a series of papers that I started writing like 3-4 years ago with Sebastian Misera. And in the meantime, other people joined for part of the fun. And yeah, so it's really going back to the roots of string theory and trying to compute amplitudes. Okay, so first, if you've never been in contact with string amplitudes at higher genus, and maybe you computed one-loop amplitudes of QFT in your QFT course, you might have the impression that in string theory it's similar, but it's much more complicated. And I think surprisingly little is known about string amplitudes at higher loops. So let's start and look at our favorite formula for the scattering amplitude of gravitons in string theory at tree level. It takes this very nice form. So there's some tensor in front that takes care of all the polarization dependence of the 2-to-2 graviton scattering. That is completely known, and it's the same at every loop order. So in some sense, it's boring. And the interesting part is this, the dependence of the amplitude of the three Mandelstam variables ST and U, and it takes this very nice form. And let me just point out some of the amazing properties. It's manifestly crossing symmetric, and it's just one term, so it's not a sum of different diagrams as you have in field theory. This is the old idea of dual resonance. It is Regge bounded in the Regge limit. It's UV soft, as we already heard previously in the conference. So if you go to very high energies at fixed angle, the amplitude decays exponentially fast. And of course, it's also consistent with unitarity. So it's actually very hard to cook up functions that do all of these things. So even if you don't know about string theory, just try to write down a function that does all of these things. And maybe you have the impression that if you go to a higher loop, there's an equally nice expression, maybe with slightly more elaborate special function, but somehow this is not really close to the truth. So today I will try to explain a general idea that we have about computing this one-loop string amplitude. And in some sense, it's a technique to compute certain integrals over modular parameters. So if you encounter an integral over a modular parameter, then you can also apply this technique, even though it has nothing to do maybe with string amplitudes. All right, so first of all, to convince you that there will be some result. So what we mostly care about is actually, getting the plot. Like if an experimentalist would ask us, like, what's the signature we should actually look for if we could build your great collider, then unfortunately the truth is that beyond tree level, we couldn't actually tell them what kind of amplitude they should look for. And so this is the plot of the one loop piece of the amplitude. So I've not plotted the tree level. This is just a one loop correction. And I plotted as a function of the energy. Here I put alpha prime to be 4, so in the previous units, just so that all the poles of the amplitude sit at integers. And you see, again, this is plotted at fixed angle, and the amplitude goes exponentially down, also at one loop. We'll talk more about this, but it has a kind of non-trivial structure to it, and the blue curve is the imaginary part, and the yellow curve is the real part. The imaginary part will be much easier to compute because it's determined by the optical theorem from tree level, whereas for the real part, we really have to work. And you see it's not perfect what we do because there's some kind of numerical error. And also, I want to mention that there has been a lot of work in the literature by these people, plus probably other people that I haven't mentioned, in trying to understand the low energy expansion of the amplitude. So if you take the amplitude, you go to low energies, meaning down here, before the first massive string state appears, then you're basically talking about Q of t with higher derivative corrections. And you can compute the amplitude systematically in this alpha prime expansion. So it's known to 7 orders or something like this. So we just took the answer that you can find in literature and you plot it, and you see that kind of reasonably fits. And for reasons I'll explain later on, this is actually the region where we have most trouble in applying our method. All right, so we'll come back to this later, but this is just a short preview. So what the talk will be about is first I will explain what's the actual integrals we need to compute, because there's some fine print in trying to define string amplitudes. Then I'll explain how this evaluation works, this Rademacher method, and then we'll talk a little bit about physics in the end. So let's get started. And so if you read any textbook on string theory, they usually tell you that a string amplitude is computed as follows, schematically. So you want to understand some endpoint amplitude at genus G. What you need to do is you need to compute some CFT correlation function of the worldsheet. There's just flat space, to be clear, and then integrate over the modular space. There might be some fine print. If you do the superstring, then you need to worry about picture numbers and so on, but let's not worry about that too much. But the thing that I want to point out is that this integral is pretty formal, because typically it's divergent. And the integral diverges from the boundaries divisors of modular space. So these are regions in modular space that describe surfaces where some part of the surface pinches, and some part becomes very long. And all these singularities, because there's a part of the surface that becomes very long, they're all IR singularities in space-time. So there's nothing to say that string theory is somehow wrong. There are no UV divergences or something, but there are many IR divergences, and they lead to physical features in the amplitudes, like poles and branch cuts and so on. Okay, so this is something that we do actually expect, because, for example, this thing is fully real. So if we integrate it, and the integral would make sense that our amplitude wouldn't have an imaginary part, which, of course, it should have. Okay, so, and there are several solutions to this, but I think a particularly nice one was discussed by Witten about 10 years ago, is that actually what you need to compute is this integral, but what you forgot in writing this prescription is you forgot that the worldsheet is actually Lorentzian. So everyone loves Euclidean 2D CFT. It's very nice and so on, but at the end of the day, we need to care about the causal structure of spacetime. And so there's a Lorentzian direction on the worldsheet. And what that means is that we should not integrate over the modular space of Euclidean Riemann surfaces, but we should integrate over some kind of modular space of Lorentzian Riemann surfaces. And what that means is, so you take the modular space, MGN, you complexify it, which means now you don't care about whether it's Euclidean or Lorentzian. It could be some complex metric on the worldsheet. And then you need to pick a particular contour in this complexified version of the moduli space that you need to integrate over. So the naive contour is that you pick the contour of the Euclidean worldsheets, but that leads to ill-defined integrals. And in fact, what Witten explained is that whenever you go close to, so this contour, this Euclidean contour is fine as long as you stay away from the boundaries of moduli space. But if you approach one of the boundaries, then you get a part of the worldsheet that becomes very long, and you can think of it as being basically a word line. If you don't look very closely, it looks like a word line in Q of t. And then we know what to do, because this moduli space, all these moduli, they become the Schwinger parameters in Q of t. And what we forgot to do is to implement the I epsilon prescription. Like Schwinger parameters are really Lorentzian, and they have some I epsilon prescription. And what that means is that this contour will get modified and goes off in some complex direction. So this is sometimes called the stringy I epsilon prescription. But it's a version of the Feynman I epsilon prescription in string theory. And in particular, that is responsible to give you all the imaginary parts and so on the amplitude. Okay, so I'll not tell you exactly how that works, but just let me tell you how it works for the one-loop amplitude. So then, well, you go and you, sorry, I should have mentioned Green and Schwarz here. So this is the classic result of Green and Schwarz for the one-loop amplitude in type 2 string theory at one loop. So they tell you, like, after you go all through all the picture changing, summing over spin structures and so forth, you get some very nice integral that you should compute at one loop that they tell you is the answer. And they also already stripped out, there's also this T8 tilde, this polarization dependence that I will just strip out because it's some overall prefactor. I only care about the actual kinematical dependence. Similarly, there's some G string to the fourth in front that I'll also forget. Okay, so they tell you you need to compute this integral. And that looks like a pretty easy task. So it's some 8-dimensional integral, so you would think, okay, just put it on computer. But in particular, we already know that the answer has this very exponentially decaying feature. But if you look at the integrand, it actually seems to be exponentially growing if you make the energy bigger and bigger. So there's some huge amount of cancellation in it. And that makes it very tricky to evaluate, say, numerically. So, and what is this I epsilon prescription doing? Let me mostly focus on this, the part of the integral that is over tau. There's also the part of the integral that is over z, but it's sort of less harmful, let's say. So in particular, in tau, we need to integrate over this fundamental domain. And so there's the CASP in the fundamental domain where we get all these divergences from. And what we need to do is sort of what is schematically drawn here. So you go to the CASP, but before you arrive at the CASP, at some point you decide, well, now your torus is very long and you're basically doing Q of t, and you need to complexify and turn off in the complex plane. What that means is you formally you take the real part of tau and the imaginary part of tau, you write the integrand as a holomorphic function x and y, in the real part and in the imaginary part, and now you complexify x and y. And you let the contour, so in x it just goes from -1/2 to 1/2, but in y it turns into the complex plane. Okay, so slightly funny because the moduli space itself is complex. So you first have to forget that the moduli space that you integrated over is complex, and then you complexify it again, and then you can go off in the complex plane. That sounds confusing. Think about the open string. In the open string, you have just a one-dimensional integral, and that integral is over the imaginary part of tau, and then you can go off in the complex plane. It's the same thing. Okay, so this is, and once you integrate over this contour, everything is convergent, because all of this stuff will be oscillatory in this direction, and there's this 1 over im tau to the 5 that makes everything converge. And you have a choice whether you come out of the board or you go in, and that's the sign of the I epsilon prescription. Okay, very good. So now we know what, in principle, the integral is that we should compute. How do we compute it? So this is still not very useful. So this is what I basically just said, that if you try to put it on a computer, well, it's convergent, but there's so much cancellation that it's the sign problem in quantum mechanics all over again. So we don't really know how to usefully put this on a computer. So instead, we'll apply a series of contour deformations, because now we have some high-dimensional contour, and we have a holomorphic integrand. It's holomorphic in this complexified sense. So we can freely move around our contours and have fun. So, and for the real part, this will be fairly difficult, but for the imaginary part, it's not so hard to understand what to do. Because for the imaginary part of the amplitude, we know there's an optical theorem. So that should be simpler. And indeed, it is. So if you want to compute only the imaginary part, what you need to do is you take the difference of the two I-epsilon prescriptions. So the one where the contour goes out of the board and the one where it goes into the board. And in this difference, the real part will cancel out and the imaginary part will add up. So if you want to compute the imaginary part, it is just computed by the contour that's schematically drawn here that goes sort of in the board. And why is this contour much simpler to evaluate than this contour? Because everything's holomorphic, so we're freely allowed to move around this contour. It's a two-dimensional contour, so it may be hard to think about. But basically what you can do is you can push it up as much as you want. You can move it as close as you want to the cusp. And what that means is that you only need to know about the local behavior of the integrand near the cusp to evaluate this integral. That's why it's easy. So let me show you at the toy example how that works. And maybe you got taught in your string theory course that you shouldn't compute one-loop determinants of the bosonic string, but it's a perfectly fine integral that you can compute, but it will turn out to have an imaginary part. So I will explain some of the techniques at this toy example, just because it's simpler. So say you want to compute this bosonic string one-loop partition function, and let's first compute the imaginary part. So then we have to compute the integral over this contour, this imaginary part contour, that's the one that goes into the board. Well, so now, because we can push it up to we can make the imaginary part of tau as big as we want, we can plug in the Q expansion of this 1 over eta to the 24. And there is the term that corresponds to the tachyon, and then there's subleading terms. And already the massless terms, they will die, because if I push this to higher and higher values of im tau, well, this 1 over im tau to the 14 will suppress me more and more. And then there are the even more subleading terms, and they will die exponentially. So they die even more. So that means it's an exact thing to just omit all these subleading terms. So we're only sensitive to terms in this integral that blow up near the cusp. So this is precisely the term that you got taught that is bad in the one-loop amplitude, because if you integrate over it, it makes it not convergent. But once you have the right contour, then, well, this is a term that has an imaginary part. Fine. And then, okay, it's kind of elementary. Then you integrate over the real part. This doesn't depend on the real part. And then if you call the imaginary part y, then some kind of elementary integral. You get some power of pi. But this is just to say that it's easy to do. Okay, so if you do this for the full amplitude, you need some extra tricks and so on. But the final result is as follows. So you want to compute the imaginary part of the amplitude. And it takes, by doing the same kind of trick and pushing it up to infinity, you pick up some number of terms. Those number of terms are labeled by the masses of sort of what we call m down and m up. So this is the amplitude, and what you will reproduce is unitarity cuts in QFT. And you can have some massive string state down here labeled by an integer md, and the mass will be square root of md. And there's some integer up here, and you need to sum over all possibilities. Then you need to integrate over the on-shell phase space. There's some gram determinant that comes from this integral. And then there's some sum over polarizations. And in principle, if you would do this in field theory, it will be incredibly complicated to work out the sum over polarizations as soon as you include massive string states. But if you derive it from the one-loop amplitude, there's a very nice generating function for the sum over polarization. So this is something that we can compute pretty high up. In particular, it's a square. So I wrote square because it's the same sum over polarizations that appears in the open string. So this part double copies from the open string. And then you get a massive version of the Veneziano amplitude for the, or Virasoro-Shapiro, sorry, for the left, and a massive version of the Virasoro-Shapiro amplitude for the right part. So this may look complicated, but everything in here is easy. And in particular, all this integral, so now it's just a two-dimensional integral, and it's absolutely convergent, and it's very easy to put in a computer. So this tells you what this blue curve is. And you see the blue curve is very much smoother than the yellow curve. And you can already see that. And just to point out, like even if you go to only s equal to 8, so we can in principle go higher. But already here, like if you would do it in field theory, you would need to care about roughly 10 to the 22 states that are being exchanged, just because the number of massive states in string theory grows pretty rapidly. Okay, but now let's come to this Rademacher story and try to evaluate the real part. And the idea is the same. So we saw that the imaginary part is kind of easy to evaluate because it's only sensitive to the behavior of the integrand near cusp of the moduli space. But the moduli space you can see has more cusps. Because so once you talk about this complexified moduli space, you can, for example, take tau to infinity, but you can take tau bar to some rational number. That's a cusp in the complexification of moduli space. And it turns out that you can evaluate the real part by knowing the behavior of the integrand near all these complexified cusps. So to explain this to you, it's a bit hard to draw 8-dimensional contours. So I will draw a 1-dimensional contour, and this is actually the one that appears for the open string. But I thought the closed string is more exciting, and it's more recent that we worked on it, so I wanted to show the pictures of the closed string. But for the open string, you would need also to compute some integral over some modular parameter, but there's a 1-dimensional integral. Whereas for the closed string, it will be a 2-dimensional integral. And what you do is some kind of series of contour deformations that Rademacher came up like 80 years ago in the context of analytic number theory. And basically what his insight was is that when you try to compute some integral over a modular parameter, so this is a 1-dimensional integral now, you can deform it into this integral that goes around these circles. Okay, this sounds very mysterious. So these circles are circles that touch the real axis at all the rational numbers, and they're all modular transformations of each other. So if you apply some SL to Z transformation to one circle, it gets mapped to other circles and so on. And they all touch each other in this nice way, and they don't overlap. They're called Ford circles. And they're very nice, but okay. But for some reason, you can deform the contour like this, and then you keep going. So this is, let's say, in the 5th step of this deformation, you go around all the circles, all the Ford circles whose denominator is at most 5. So you go, so here's a big circle, it's the 0, 1 circle, so you follow that one until you hit the 1/5 circle, you go around the 1/5 circle, and until you hit the 1/4 circle, you go around that, so 1/3, 2/5, and then 1/2. You do the next step, then you also need to go have this small dent in here in the contour and so on, okay? So, and then you keep doing this procedure, and you cross your fingers, and you hope that it converges, and you take everything to infinity. And in the limit, your contour goes around every one of these circles exactly once. So you can already see here, it almost goes around the 1/2 circle almost completely. If you go further and further and further, it will go more and more around all these circles. And then the point is that once you go have the contour as a sum of these circles, well, all these circles, I told you, are modular transforms of each other. So in particular, you can, if you want, you can map them to a horizontal contour, and then you can push that back up to infinity, or you can also say, well, you can shrink these circles, right? It almost seems like this contour should give 0 because it's contractible. But because the integrand has an essential singularity here, it's doesn't give 0. But you can make the circle as small as you want, and you're only sensitive to the local behavior of the integrand near these rational numbers. Okay, and then those are kind of similar to evaluate as the imaginary part. So now we want to apply this for the closed string, and I'll explain again at the example of this toy example how that works. So what we want to compute now is this integral, this one-loop partition function over this funny contour. And the goal is to evaluate it in terms of its behavior near all these complexified cusps. And by that, so now you have tau and tau tilde. Tau tilde I call minus tau bar, so that's also in the upper half plane. So both, they live in the complexified version of moduli space, which is 2 copies of the upper half plane, modded out by 1 copy of PZ2Z. And so what we need for this is a 2-dimensional version of the Rademacher expansion. And because it's a 2-dimensional contour. So this was not available in the math literature, but fortunately Tom Hartman and student Jeevan Chandra, they told us a trick. This is basically some kind of version of the Lorentzian inversion formula in 2D CFTs that allows you to holomorphically split the tau and tau bar variable, and then you can apply Rademacher expansions on those separately. And so ultimately, after some steps of contour deformation, you come up with this formula. So it's a quite general formula that works whenever you want to compute an integral of a non-holomorphic function over the fundamental domain. So I'll just state it for the real part, because for the imaginary part, again, it's easy. And the real part of this answer is evaluated as an infinite sum. And this infinite sum is just a complicated way of saying all the fractions between 0 and 1. So the c is the denominator of the fraction, and a is the numerator. It goes from 0 to c minus 1, and it needs to be co-prime. And then you get contributions from all these circles. So because it's invariant in the modular transformation, you can always map this circle to be the horizontal one, which is like the fourth circle around infinity if you want, and the other one, all these circles at all these rational numbers that we just had. And then there's some extra factor here. So this, in particular, there's some number here. This is the Dedekind sum, is some number theoretic thing that you don't need to care about. It's just basically measuring some kind of multiplicity of these of this contour inside the initial contour. And there's also some simple extra factor here. And unfortunately, I won't have time to tell you the full proof, but I encourage you. It's kind of fun to go to look at the paper. Yeah, so it's some combination of Lorentzian inversion formula and Rademacher expansion that ultimately gives you that. So once you have this, you can, for example, apply it to the toy example. And what you find if you just plug it into this formula, well, the point is that the integrals on the right-hand side are easy to do because you can shrink them. So they're only sensitive to the local behavior. And you can just fully evaluate it. So what appears are some Bessel function here. And there are some phases. So A star is the modular inverse of A mod C. And this is a very rapidly convergent sum. And then, of course, you have the imaginary part that we computed before. And I should really mention that this works in principle for any modular invariant function, provided it satisfies a certain boundedness condition. So modular invariant function that you need to analytically continue in terms of tau and tau bar. And it needs to satisfy some boundedness condition which is needed for this to converge. So basically, yeah. So, but the kind of integrals that we have here do satisfy this. All right. So, and then we apply this for the full string amplitude. Then it becomes a little bit more complicated, but you still get the sum over fractions. You get also additional sums because there's also the z integral. So there's some sum over some kind of winding. And then you get these building blocks, and each of these building blocks is kind of manageable. And that is our formula. So it looks kind of complicated in the end, but I promise it's better than the initial integral that you write down in the beginning. And in particular, it's a convergent representation of the amplitude. And it's kind of practical to put on a computer for roughly this range of S. So it depends a little bit if you want to compute the full amplitude, and roughly we can go to S equal to 10. If you want to compute some special things like decay with mass shift and so on, we can go higher. For very small s, it turns out that the convergence breaks down. And the reason for this is that the amplitude has a massless branch cut that is not manifest in our formula, and it manifests itself by the sum over c over all the fractions breaking down. That's why in the initial plot, the region for very low energy is actually much worse. But there we can do direct numerical integration. There it's pretty good, or alpha prime expansion. OK, so now let's talk about physics. And let's start by computing the amplitude in the forward limit. So this is a similar plot as the one I showed you in the beginning. But now we put t to 0 and just plot in terms of s. And we also multiply by the sine pi s squared. This is just because the amplitude has double poles at all the integers. So we multiply by the sine pi s squared to get nice plots. So this amplitude asymptotically goes like 1 over s, roughly. So that's why we multiply by s. This is something that we know from Regge physics. Regge physics, this is the Regge limit for very large s. And Regge physics tells us that, first of all, the amplitude is mostly imaginary for large s. And it is also goes like 1 over s. And this is asymptotic. You see it's actually very bad. The reason for this is that the error is of order 1 over log s. So you need to go to extremely high s to actually see that. Which we can do for the imaginary part, but not really for the real part. But everything that we find here is consistent with the expectation from Regge physics. In particular, these Regge asymptotics were worked out a very long time ago by Amati, Cefaloni, Veneziano, and also Bo-Sundburg. Maybe this is very similar in some sense to QFT, because all this Regge boundedness is also true in QFT. But what's very different is these fixed angle scatterings. So this is, again, the same plot as in the beginning. And in particular, for very large energies, there's this expectation from Gross-Mende that you get this exponential decay. But to my knowledge, this has never been checked or made precise, and with all the numerical factors. and as I want to convince you, it's also not quite true what they write in the paper. I mean, it's morally true, so you get this exponential decay, but you see there's a lot of structure on top of it. So what they correctly predict is sort of the envelope of the answer, but not the actual answer. And importantly, the exponential decay, if you were to draw the tree-level answer, the exponential decay here is actually half as fast as for the tree level. So the higher in loop you go, the less the exponential decay is. And the reason is because, so this comes because you do the moduli space integral by a saddle point approximation, and the saddle at one loop is a double cover. So the four-punctured torus is a double cover of a four-punctured sphere, which is the saddle at tree level. And the reason that is half comes because it's a double cover. Yeah, and just to plot this in a different way, so for example, we can compute this decay width to very high order and divide them by the prediction of Gross and Mende, and you see it's order 1, this plot, but it has a lot of feature on top, again, that's not captured. And we understand why that is, because there are many other saddles that were not taken into account in Gross Mende, which are not on the real part of moduli space, but they sit somewhere off in the complexification of moduli space, and they do also contribute to this answer. And so if you want to have, so qualitatively Gross and Mende is right, but quantitatively you need to include various other saddles to get actually matching numbers. So that's we're working on currently, so stay tuned for that. Okay, so that brings me to the end. So let me summarize what was going on. So the main message I want to convey is that somehow people haven't played a lot with contour deformations in string perturbation theory, and they're very powerful, these techniques. And they allow you sometimes to get exact evaluation of string amplitudes. In particular, it's numerically very useful because it kind of avoids this exponentially cancellation that you have in the explicit explicit integrals that like Green and Schwartz wrote 40 years ago. And to evaluate these integrals by these contour deformation methods, you only need the behavior of the integrand near the Lorentzian cusps, which I drew here in the background. If you stare precisely, so that's the picture you have in mind, and you can shrink all these circles, and all the integrals over all these circles are only sensitive to what happens very close to the real axis. And these formulas make a lot of analytic structure manifest, not all. For example, the massless branch cut is not manifest, but a lot of massive analytic structure is made manifest, and it in particular allows us to make contact and check this high energy Gross-Mende limit. So thanks a lot for your attention.
Questions?
So is there some way of thinking about the structure that you find on top of Gross-Mende as like quantum corrections away from the saddle point? Or?
No, it's generally different saddle points. So there's more than one saddle point. So there's the Gross-Mende saddle is this double cover of the sphere. But then there is a sort of complex, it's hard to picture because it lives in this complexification of moduli space. So it's not a Riemann surface, but it's a complexification of that. So roughly speaking, the left moduli can be different from the right moduli in these other saddle points. Yeah, I don't know how to. Something like this, but much milder already happens at tree level. That if you take Gross-Mende at tree level, you would not see, like, for example, the poles at all the integers. They come in some sense because you go on the different sheets. So the integrand, let's say you do the Veneziano amplitude, is like z to the minus s, 1 minus z to the minus t. And it has branch cuts once you are willing to complexify that. If you go around these branch cuts, you pick up various phases. And when you resum the phases, you can get correctly the poles. Yeah, and something similar happens, but it's more drastic. It's not just phases. No, the multiplicities are not clear. They follow ultimately from like all this Rademacher discussion. But it's so if you're a completely honest person, you would need to first determine what are all the left shift symbols, steepest descent contours, and so on. And that's an absolute mess. So in particular, there are infinite number of saddle points and so on. So I don't know how to do that. Yeah, so the answer clearly says, for example, there's also the main saddle, the one that Gross and Mende have, it appears 3 times, which you can roughly see from here. So there's some multiplicity of the saddles.
Can you obtain some useful information about tree-level amplitudes with some massive external states from this information on the cuts that you have?
Depends what some useful information is, I think. But the answer here is always written as a sum of all the polarizations in the middle. So it's not that you can pick out one state and talk about that, because of course that will be very complicated because it has a huge polarization tensor as an external state. Yeah, so in some sense this is an average over many heavy tree-level amplitudes because you're summing over all of them. Yeah, going the other way around is kind of difficult. Like, I mean, if you were actually to construct all these tree-level amplitudes with massive states, it's kind of a mess. Yeah.
More questions? Please, Arkady.
Is there a useful way to isolate, say, loop of massless states and then expand the rest in alpha prime expansion? So suppose we're interested in something like, I don't know, comparing to low energy physics.
Yeah. Yeah, we tried, and I don't know of a useful way, but I will be happy if there is. But, yeah. Yeah. Yeah, I would be very, in particular, it's very hard for us to do analytically this alpha prime expansion of the answer and connect to it back. So it will be fantastic if we sort of can take out the massless part, which ironically for us is the hardest, and then do this and then somehow put it back at the end. But yeah, I don't know how.
So if there are no more questions, I have a little question. So if we have a function of one complex variable, we know what is the deformation of contour. It's because we assume that the function is analytic. But what does guarantee, or at least hints on this double analyticity, both in real and complex part?
Yeah, so for this integrand that is of interest here, it's just 2, because it has a very nice Q expansion and so on. So you need to assume for this formula to be true that the integrand, first of all, extends analytically in both tau and tau bar, or tau tilde as a holomorphic function in the full upper half plane. And so almost all the functions that we have, they have nice Q expansions. So whenever you have some Q expansion of some conformal field theory or something, it converges absolutely even if you make Q and Q bar independent, right? So for all these functions, will always be true, but it might be that you can come up with some kind of pathological function that, are you worried about several complex variables? I mean, there can be funny phenomena happening, but
it's a bit funny that you take real and imaginary part separately and then announce that even in those variables it's analytic.
Yeah, I agree, but in some sense it's an accident that the original modular space was complex, so you could forget about the fact that the modular space was complex, because, I mean, if you have Lorentzian 2D surfaces, of course they won't be complex. They don't, yeah.
Okay, thanks. So if there are no more questions, let's thank again Lawrence.
Thanks.
Yeah, maybe people are still There is some point where Nikolay would do like that, right, outside, so so we will see all people.
It's okay, don't swear.
I didn't say anything wrong. Is it too high? Is it too high, the volume?
No, I think it's
okay?
perfect. Yeah. Sounds good.
Okay, so welcome back, everyone, to the afternoon session. So as you know, we will have a talk now, coffee break, and then we have another gong session after with short talks. So yesterday, Nadav reminded us of the enormous prestige of this institution. And today we have another asset of the institution, which is Paula Ruggiero. And she's going to talk to us about full counting statistics after quantum quenches as hydrodynamic fluctuations.
Thank you, Elijah. Thank you, Nadav, for reminding about that. And thank you very much for the invitation to this nice conference. So, yeah, this talk is probably a bit different from like an average talk of this conference. I hope, so feel free just to ask anytime. And yeah, so this is work in collaboration with other people at King's, in fact. So Benjamin Doyon, is a professor at King's, and David Horvat, who is a postdoc here. Okay, so this is the outline of the talk. So in the first part, I will spend actually some time here talking about, in general, fluctuation and the relation to full counting statistics, and what we know about that already. In particular, I will say something more specifically in the ballistic regime. And then the second part is to do more about our work, which is about full counting statistics in some auto-equilibrium setting, in particular after quantum quench, which I will introduce. So, okay, we can start with the first part. So let me start with some introduction and motivation. So this talk is about large-scale fluctuations. And we want to study them in the context of many-body system, let's say for now, to stay general. And what is true is that all many-body systems, basically all of them, admit at least a few conserved quantities. So the easiest thing you can think about is a gas of particles where a particle number is conserved, for example. But of course, if you now restrict one of these conserved quantity of conserved charge, we'll call it as well, to a subsystem, this is clearly not conserved anymore. Again, in this example, just because a particle go in and out, so it's not conserved. And so this restricted quantity is not fully characterized by its mean value, but fluctuates instead. And to fully characterize it, we need to know all its cumulants, which are related to the connected correlation function of endpoint correlation function of this quantity. And such cumulants are generated by this object called full counting statistics, which is this function f of lambda, which is the logarithm of expectation value of e to the lambda, this charge restricted to the subsystem. And this quantity is, you may know, so it generates all the cumulant by a Taylor expansion, or just deriving with respect to lambda, putting lambda equal to 0. So why are fluctuations interesting on a large scale, where here by large scale I will mean both like in space and in time? It is because they encode universal properties, okay? So for example, as I will say in a while, at equilibrium, they don't depend on all the details of the system itself, right? But just on thermodynamic function like macroscopic variables. Okay, and basically, most of what we know about that is based on the large deviation principle. So the statement of the large deviation principle is that if you consider an extensive observable, here I mean extensive in a generalized sense, so this observable just scales in some way with the space x and time t, then the probability for this observable to take some value which is different from its mean value, basically decay exponentially in this way, okay, with this scale here, and this function is called as a rate function. And this is like the main object we would like to study, but in many cases it's actually easier to study instead its Legendre transform, which is called full counting statistics, okay? And in this large x and t regime, this is defined in this, through this limit here. So without being very precise, let's say that in general for an ergodic system with a local interaction, such a large deviation principle is expected to hold, but in fact it's rarely proven. And especially if you are looking at hydrodynamic observable like charge densities or current, as I will be interested, this is even expected to hold even more widely in a sense. And also observation though is that, so this principle gives, if you want, the form, right, both of the probability and the full counting statistics, but actually if you want to compute them explicitly, you need to combine it with other tools, right, so it's not enough. Okay, so, and to say a bit something more about what we know for now about these full counting statistics, let me be a bit more specific than generic many-body system. So now we restrict to one-dimensional homogeneous quantum system with local interactions. And we assume that this system will, for this system to have n conserved quantities, which are assumed to be local or quasi-local. And in particular, what I mean by that is just that these charges are written as the integral over some density, and this density satisfies a continuity equation with together with this to the associated current. And okay, in this audience probably is not, I don't need to say, but n in general is, so the number of conserved quantity in a system in general is small, right, 2, 3. But for integrable system, instead, it's infinite. And a special subset of states that will play like a main role for what I'm gonna say later are steady states. So those are the states that are expected to, at some point, to arise after some long-term dynamics. And to this state, so part of these states are the so-called maximal entropy states, okay, which are, for example, Gibbs ensemble or generalized Gibbs ensemble for integrable models, and they are specified by a vector beta, whose component is the same number as the number of conserved quantities, and formally these states are defined by these density metrics. So according to the fact that they are maximal entropy states, they're just the exponential sum over I beta I qi, with this beta I playing the role of a Lagrange multiplier. But also, these are not the only ones. So also, steady state are also not just equilibrium steady state like this kind, these GGEs, but also non-equilibrium steady states, or NES, which are states a bit more general that can sustain persistent non-zero currents. So they will also play a role later on. Yes, and so what do we know about full counting statistics in different settings? So let's start with the easiest problem, which is considering some static quantity on some large region in some steady state, or more specifically at equilibrium. So in this case, it is known, actually, I mean, in different contexts, in different communities, but since quite a long time, that in this case, thermodynamics is enough to describe full counting statistics. And what I mean by that is the following: is that if you consider a charge restricted to some large subspace, so here 0x, and you define the associated full counting statistics. Here I'm assuming that the scaling is just, so Q of x is just a scale like x itself. Then this is just given by a difference of free energies, right? So in this sense, it's just characterized by the thermodynamic properties of the system, where you see in the first, so here I'm just highlighting the fact that the difference between these two free energies, that in the second one, the Lagrange multiplier associated to the charge I'm considering is shifted by lambda, lambda being this parameter entering, this counting field entering in the full counting statistics. Yeah, and this free energy, of course, is related to the steady state I'm interested in this way, right? So this is the relation. Okay, the next step is what about, so we consider dynamical quantities on a larger time interval, but still in a steady state. So in this case, I mean, thermodynamics, of course, since we are starting to go towards the dynamics in a sense, is not enough. But in some cases, it's known that now what we need instead is the hydrodynamic data. And so more specifically, say that you want to look to some charge passing through some interface like x equals 0 for some long time. Then the full counting statistics take this form, where now here I'm allowing some more general scaling with time, and the scaling here is of course fixed by the transport properties, basically, of the system one is looking at. So in particular, if a system sustains ballistic transport, this corresponds to alpha equal 1. And this is the case, for example, for integrable models, that what we expect, ballistic transport. And in this case, so in order to know this quantity, what we need to know is Euler hydrodynamics, and so the explicit form of this quantity is given, so using this Euler hydrodynamics by the so-called ballistic fluctuation theory, which is quite a recent framework. I will talk about that more specifically in next slide. Another important case is for alpha equal 1/2, which is the diffusive scaling. And in this case, the theory that allows us to fix the properties of this full counting statistics is MFT, or macroscopic fluctuation theory. And then, okay, in general, transport is called anomalous for generic values of alpha. For example, alpha equal 1/3 is the so-called KPZ scaling. But in general, for generic alpha, the large radiation principle itself can be broken in some cases, so we don't have like results for generic alpha. So the following step is that what I was talking about here was always looking at expectation values in a homogeneous steady state. But in fact, one can extend at least to slowly varying states, okay? And this is because, at least locally, they are still maximal entropy states, and so we expect hydrodynamics to still hold, okay? Instead, a big step, like with respect to this example here, is if we ask ourselves, what about if we are truly far from equilibrium? So in this case, massless is known, and so our work, I mean, is in this context. So this is what I will talk about in the second part of the talk, basically. But before that, I want to say just 2 slides about. We're still in the context of steady state, or at least a slowly varying state, in the ballistic regime, because these I will use in the following. So again, consider one of the charge of a system with the density and the current given by Q and J. So in the previous slide, I talked mostly just about either a current in a big interval, or sorry, a charge in a big interval, or a current in an interval of time. But more generally, one can consider, it's convenient to consider what I will call as generalized 2 current, which is an object. Basically, I can consider a more general path from 2 points in space-time, 0, 0, and xt, and define this object, which basically, I mean, if you just consider an horizontal path, this just goes back to the case of a charge in a subsystem, and the vertical path instead gives just the current in a time interval. But you can consider this more generic object. And in the ballistic regime, so we know that we expect time and space and time to scale in the same way, so we can introduce a unique scale, L. And we expect this generalized 2 current is delta J to scale like L, and therefore the full counting statistic in this case is defined as the limit of the scale L going to infinity. So what this theory that I was mentioning before of this ballistic fluctuation theory gives is a prediction for this full counting statistic f of lambda, and just give you the result mostly. So this is the result is basically an integral over a flow in lambda. So we have these generalized 2 current, so evaluated in a state which is lambda dependent, and in particular is nothing but the steady state we're interested in, so multiplied, so biased by this e to the lambda delta j. So maybe it's more useful to look at an explicit example. So instead of considering a generic path, consider a segment path of this kind. In this case, f of lambda takes this form, and here you can see clearly that basically this is completely fixed by if we know the expectation value of j and q in this state. And so we only need, so these are exactly what I mean by hydrodynamic data. So if we know the hydrodynamic theory, we know this expectation value, and so we know this f of lambda. And this is the case for integrable models, because in this case we do know the hydrodynamic theory associated, which is called what is called generalized hydrodynamics. I won't tell much more about that. Instead, I just want to make an important observation, which is the following. So this result, and also the ones in the previous slides, basically we were all the time talking about steady state or maximal entropy states even. So why was that? So here, for this result to hold, for example, a key assumption is that along the integration path, one assumes that there are no strong correlation among those points, okay? And this is just true in most steady states. that's why most of the results that we have are in this case, okay? This instead is not true out of equilibrium, which is what I'm gonna tell now. So now in the second part, I'm gonna talk instead about how to characterize this full counting statistics out of equilibrium. So an easy way to go out of equilibrium is to consider this quantum quench protocol. Yes?
So what's like the status of the statistics?
Well, I mean, this was meant to be kind of the status of things. So in steady states or slowly varying state, okay? This is kind of we do understand. So if you just look at equilibrium, this kind of old results, though in different communities were understood in different times. If you go to dynamical quantities, it's more recent results, in fact, already, and even more recent this extension to slowly varying state. Instead, out of equilibrium, we don't know much, so what I'm going to talk about is about that. So what our contribution, our basically the paper that I was mentioning at the beginning are about that. This a specific out of equilibrium setting, which I'm going to introduce now.
Yeah, but my question is like,
Like, it depends on how rigorous you mean. No, I mean, yeah. If you want, well, yeah. So sort of like this paper are a sort of rigorous paper, for example. Out of equilibrium, sorry, for dynamical quantities. Yeah, I mean, like exact result, but not rigorous. I would say, okay, exact but not rigorous. Already, if we go to currents, for example. But I mean, some results, for example, are in this review, and which is quite rigorous. Okay. Yes. Yeah. I don't have a specific answer, to be honest, to that. Like, yeah. It's also a bit model dependent, and whether there are specific results. But I would just say that at equilibrium, in steady state, the situation is clear what's happening. Okay. Instead, out of equilibrium, it's very different, and I'm gonna now explain why. What is the big difference here? So first of all, for those of you who might not be familiar with, let me just say what is the so how do we generate the out of equilibrium dynamics, basically. So the easiest way of doing that, that's why we consider that, is through a quantum quench protocol. So the most general definition of that being that we initialize the state in some initial state psi 0, which is not an eigenstate of the Hamiltonian which governs the evolution, and not even an easy superposition of few eigenstates, so that really when we let it evolve, or like according to Schrödinger equation with the Hamiltonian, it will really evolve. And what we know in general about quantum quench is that at long time, thermalization or generalized thermalization, depending on whether the model is integrable or not, is expected, meaning that local observables are expected to be described by a steady state. So here it's important that this holds for basically for one point function, okay, so local observables. And instead, the same steady state is not enough if we want to describe fluctuation. This is because steady state usually they don't have the information about long-range correlation. Okay. On the other hand, long-range correlation are expected to arise after a quench, and an easy way to visualize that is to think about this initial state at time 0 plus, let's say, right after the evolution has started. This can be seen as so the initial state can be sort of seen as a source of entangled pair of particles So this is particularly true in the case of integrable models, where really you can think really about the state as being a source of pairs of particles with opposite momentum. This is called also quasi-particle picture. And this is, this is also true specifically for what we refer to as integrable quenches, which means quenches from specific initial states where the only correlation are due to these pairs. So more generally, you can have some multiplets or some other kind of correlation, right? But in integrable quenches, they really have this structure here, and they can, in fact, written in this way, where kind of a la Bogoliubov, where it's clear that it describes particles with opposite momentum. But okay, if we want to be a bit more general, even if we are not talking about integrable models, the quasi-particle concept can be replaced by the concept of hydrodynamic modes, but okay, I won't talk about that. Okay, so let's come to the full counting statistics after a quench. What can we say about that? So here I will consider just 1D interacting integrable models, and I will restrict to these integrable quenches, which I just introduced. Though, many things can be generalized in general in the presence of ballistic transport. And as charge, it's good to think about the particle number, though again, it's easy to generalize to local charges. And the object of interest in this case is this one. So we are interested in studying the given charge restricted to some subsystem X after some time, large time t after the dynamics, starting from the state psi, okay? And we are interested in ballistic regimes, so both X and T scale like L, and that goes to infinity. So the easiest regime is where, L and T are both large, but still X is much smaller than T. Since time is large, basically one can assume that psi is relaxed to a steady state. And as I said before, this is basically, at this point, everything is fixed by thermodynamics, and this full counting statistics is given as a difference of free energy. Where X and T are comparable, of course, is the most difficult regime. Instead, our result that I'm going to talk about in the next slide is about the regime where T is much smaller than X. So we are basically here, right? So this is the easy regime. This is like an intermediate regime, which is the most difficult. And this is what we're going to talk about, where time is small, but it's still macroscopic, okay? Because we are in this ballistic scaling. And so, and this makes the problem non-trivial, because in this small time, we cannot forget about this correlation that I was mentioning before. So I will start by showing and comment and make some comment about the result, and then I will go quickly through how to derive it. So what we can show is basically that this full counting statistics takes this asymptotic form. So you see there is a linear term in X plus correction that just depend on X, a linear term in T that just plus a linear plus correction that just depend on T, plus a term that goes to 0 when X goes to infinity for every time. And the most interesting object is basically this coefficient in front of the growth in time, which is what we can characterize, in fact. And it turns out that this quantity here can be seen itself as the full counting statistics of the current corresponding to the charge we are originally interested in, but this is evaluated in a non-equilibrium steady state. Okay, so and this is the picture to understand what is this non-equilibrium steady state. So the non-equilibrium steady state, this nest, is what emerged here at large time along this ray x equals 0 from an inhomogeneous bipartite quench, basically the situation where on the left, we have our original initial state psi, and on the right, we have a biased version of it by e to the lambda half q, where q is the charge of interest. And so if we just join these two systems, so some dynamics will happen, and we expect here some nest to emerge. And this is the nest we are talking about here. But the physical intuition is also that one can think as follows. So one can think that this vector psi, after some time, will evolve to a GGE, and the same is true for this other state here. Will evolve to another GGE here, and these two GGE now, if you let them evolve, they also will generate a nest there, and so the two nests are the same nest basically. In the case of integrable quenches, we are also able to characterize explicitly what is this GGE of this bias state here, which is the original GGE of the state psi, plus 2 lambda q, the charge, and this can be shown using quenchuction methods. But an important consideration, an important feature of this result is that we started by considering the full counting statistics of an homogeneous problem. So the system is translational invariant, and we want to study just the charge after some time. And in the result, we end up instead, so in our result, we end up instead with an inhomogeneous setting, okay, which is a bit odd at this point, so it's not clear where it comes from. Hopefully it will be clear through the derivation, but this is an important, an interesting observation. And the other thing is that if we assume that in this nest there are no long-range correlation like in time, then you can use this ballistic fluctuation theory even if you are not like at equilibrium. And in this way we have an explicit expression for this F dynamical. And it turns out that this reproduces a conjecture that was put forward for generic integrable models, but coming from a completely different approach, which is known as space-time duality, which is at the level of a conjecture, but was shown explicitly for a model which was also mentioned yesterday, this cellular automaton model Rule 54. What is interesting, I think, of our work is that, so two things mostly. One is that we derive this result just using very simple hydrodynamic-based arguments, which makes kind of a bit the physics more transparent. And the other thing is that, so this was a general conjecture for all integrable models. But in fact, through these hydrodynamic-based arguments, we can show that there are physically relevant cases where this formula is not exact, in fact. So the conjecture is not true. It's not true in general, but I won't have time to discuss that in this talk. So yeah, so in the remaining 5 minutes, I will just sketch basically how to get to this result, okay? So the asymptotic form is kind of, it's sort of simple to understand. It's just, so this is the log of that is the quantity we're interested in, right? This F. So we just multiply it by the same quantity but at time equals 0. And if we just using large deviation principle with a linear scaling, which is typical of the ballistic regime, so is what we expect. So this bit is expected to give the linear term in X, and this term is expected to leave the linear term in T, okay? So this just gives our asymptotic form. And with the proper limit, one can extract these two coefficients, which were appearing in the formula here. In particular, this ratio here of the charge at time t over the charge at time 0 is what gives the dynamical bit that we are interested in, okay? And specifically, the limit is first x going to infinity, and then time goes to infinity. So, okay, so the first point of this hydrodynamic argument is the following. So the main problem for doing this calculation is that accounting for this long range correlation in a direct way is difficult, because all the results I showed you were based on the fact that there are no such correlations, okay? So the idea is that, the main idea is that if we are able to avoid them somehow, then maybe we can still apply ballistic fluctuation theory even if we are not in a steady state, okay? And if we look at charges, this is possible in the following way. So we can use the continuity equation to turn this path here, describing the charge at time t in an interval x. We can, using the continuity equation, we can just deform it basically as we want. And in particular, we're going to deform it like that, okay? So we're going to write that as the sum of these 3 bits, okay? These are the 2 currents, the vertical path, and this is the charge at time 0. And the idea is that maybe along this path now, we are in such a situation that these long-range correlations do not contribute, and so we can use ballistic fluctuation theory. Okay, so this is the main idea. The second step is to consider the large x limit, and in the large x limit, the idea is that this full object here, okay, so the exponential of these two generalized 2 current here, basically decompose into the product of the left and right contribution. Okay, I don't have time to go into the details, but mostly the assumption here is that the left and right operator commute, and that the state psi is clustering, and then basically you can write that as the product of the left and right bit. And so now you can just focus on one of these 2 bits. And now the third step is the large t limit, and the idea here is that, so now we concentrate on one of these bit here, so using some property that we call asymptotic commutativity, which is actually non-trivial, but which basically allows you to write the exponential of a sum as product of exponential and just reshuffle them mostly. Now this object here you want to interpret as the expectation value of e to the lambda j, so the full counting statistic of the current, in this new state here, which now is an inhomogeneous state, is where this inhomogeneities come from, because this charge here is just act on 0 infinity. So this is the state. On the left is the original state. On the right is biased by this e to the lambda half q. Okay. So we rewrote the problem as a problem of a bipartite quench in this now inhomogeneous initial state. And the last step now is that if we start now, if you imagine now our dynamics from this inhomogeneous state, and we look at the current, so the full counting statistic of the current now along this ray, at large time we would like to replace the initial state by the Ness emerging at long time. This is one step, and assuming no correlation along this path, then we can use ballistic fluctuation to evaluate that, and this gives the full result. So this is done again by there is some assumption, of course, that we do, but a very physical assumption. Mostly that so we do assume that this inhomogeneous state converge to an S there, at least for local observables, and that this initial state itself, if we look at time correlation of current at different times, they decay fast enough, where fast enough depends on the problem, let's say. And this is a non-trivial statement, actually. This is a bit the tricky part. But okay, if you assume that, then we have our full result. And okay, and this brings me to the conclusion. So we'll just summarize basically what I said. So what I showed is that by using just hydrodynamic-based arguments, we can derive a formula for the full counting statistic of a charge at large time after an integrable quench. which is valid in the ballistic regime, in particular when x is much larger than t. And an important physical point is that the arguments show how fluctuations are related to the physics of hydrodynamic long-range correlations. And also an interesting point that I don't have time to discuss here, and I mentioned already, is that that formula that was given as a general conjecture is not that general as we think, because there are physical relevant situations where it doesn't hold, and it is modified by further long-range effects, which were neglected up to now in literature. And with that, I thank you for the attention.
Thank you very much. Are there any questions? At the back there, and here as well.
As I understood, you were talking about some universal behavior of such.
Sorry?
As I understood, you were talking about some universal behavior of some systems, but is it possible to check the statements you mentioned for some specific integrable models, like besides free Fermats or Rule 54 you mentioned?
Yeah, that's a good point. In fact, I mean, this is one of the important, like, more interesting part, I think, but to get there, I needed all this bit. So let's say that this formula is very simple. It's based on very simple arguments, and it's very easy that it doesn't hold in many cases, in fact. So it was shown, in fact, in Rule 54. We showed like all the steps of the derivation in free Fermats, in different kind of free Fermat models, for example, assuming or not Lieb-Robinson bound. So what we show explicitly is a bit the opposite. So that so we give an easy example, which is a Lieb linear, where this formula doesn't hold. So if you start from a BC initial state and you quench like in the interaction strength of the Lieb linear, this doesn't hold. So the argument, many things go through. So they are quite general. The main point where this thing breaks down is this assumption here, basically. So the assumption is that in this inhomogeneous state here, one has to assume that correlation at different time along this ray, they decay fast enough. Well, fast enough depends which cumulants you want to use the full quantity statistic for. And this, in many cases, is not true, because it's not enough to assume that local observable converge to Ness to say that that basically I can So let's say that even if local observables converge to Ness, so in principle here you would think that you can in fact substitute the initial state with the Ness, like this step here. This is like the crucial point. This is not enough for the cumulants to converge to the Ness, because the cumulants are the integrated version, right, of the correlation function. So even if the correlation function themselves they do converge to the Ness, what happens is that the correction in the cumulants can give some correction in the linear scaling of the cumulants.
Okay, thank you.
So it seems like many of your arguments only use kind of like a very basic principle, like a maximum entropy and hydrodynamics. So do they generalize to higher dimensions as well?
Mm-hmm. Yeah, good question. I'm a very 1D person, I have to admit, but okay. I don't know. I mean, for example, let's say that what I know is that before going to out of equilibrium, right? So ballistic fluctuation theory does generalize to higher dimension. But here, I mean, what we have in mind is a bit of a specific setting, even if the arguments are general, but already when we talk about ballistic, I mean, I say very generally ballistic transport, but in practice, right? In practice means the integrable models or free Fermats or specific observables, right? So the arguments are general in a sense, but very specific on another, I think, maybe. But it's a good question. I didn't really think about that. Yeah, but it's interesting.
Okay, if I can, I also have 1D question then.
Okay.
So, especially for the case of quench, what happens if you consider 1 plus 1D 2D CFT? 1 plus 1D CFT?
Well, actually, in 2D CFT, this was already, I mean, it's simpler, let's say. It's even simpler. But things should work. I mean, yeah, okay. So before going out of equilibrium, so basically, so let me go to the beginning. Yeah, here. So this kind of statement that the ERA make in general, this was first understood for CFTs, in fact, by Denis Bernard and Benjamin Doyon, for example. So now what we do is kind of, I think that includes already the case of 2D CFT. So we didn't go specifically to look about that, but yeah, I would say it's included into that. Yeah.
Any more? Can I ask one? We went on a little bit, but I'm curious. So one thing that you mentioned in your answer to the first question is this idea of decaying fast enough or slow enough?
Yes, yeah.
And how that varies by operator, by theory. So can you quantify that precisely?
Yeah, so the reason why we don't
find a bound or something like that.
Yeah, so the reason why we don't quantify that enough is because this depends what is your goal in a sense, because at the end we compute in physical terms. We're interested to the full counting statistics because we're interested in 2 cumulants, right? So let's say that you want to describe the third cumulant. Then third cumulant, you would need that to go with a given, at least with a given power, for example, right? But if you are interested in higher cumulants, then maybe you need more.
But does that mean that, for example, in Liebling, you might have some cumulants and fields for which this works? And others for which
yes.
Okay.
It can be the case. It's just that, I mean, what we had in mind, for example, was just the charges. Usually it is just the
conserved charge.
Yeah, the U1 charge. So, but yeah, in principle, yes. Yeah.
Okay, I think that's all for now. So thank you very much. We should be back at 3:10, I think, for the Gong session.
And Gong-Show speakers, please come to the stage around 3:05. Thanks. Now it's on.
Yeah. So is it time? I guess it is. Let me check the time. Okay, 12. Okay, so welcome back. Welcome to the Gong sessions of this afternoon. So our first talk is by Vera Posch, and she's going to speak about all 4x4 solutions of the quantum Yang-Baxter equation.
Yeah, thank you. Okay, first of course, thank you that I get to present my work here that I did together with my advisor, Marius. Okay. What am I going to talk about? So I want to tell you about all 4x4 solutions to the quantum Yang-Baxter equation. So I'll have to remind you what's the Yang-Baxter equation. It's this. Then I have to tell you how we solved it. Then I have to show you our solutions. And then I'm going to switch gears a little bit and talk a little bit about relations between R matrices and lax operators and how these relations break, leading to the modified Yang-Baxter equation. Okay, so we said this is the Yang-Baxter equation. This is also it, but as an equation. And R, we know, is some operator from a tensor product of vector spaces to themselves. For us, this vector space is C2, therefore 4x4 solutions. R also depends on some spectral parameters, which are just some complex numbers, but importantly, they're non-physical, so we want our equations to hold for any value of them. The first thing you could try when you want to solve this is put all these parameters to be equal, which we would call a constant solution. Luckily for us, these solutions have already been classified in 1992. Luckily, because we're actually not that interested in constant solutions, but they're very practical because we can expand around them in the spectral parameters. So in short, what we more or less did was expand around these constant solutions, plug it in, solve order by order. Very simply said. The most common and best studied solutions are called regular solutions, and they're defined by setting this constant R0 in the beginning to be the permutation matrix. In the 4x4 setting, these solutions have already been classified by Marius and Luke, which are here somewhere. Of course, the regular solutions are also probably your favorite solutions, like XXX, XXZ. They correspond to regular solutions. Still, we wanted to complete this classification by now also saying, okay, what happens if this is something else than the permutation matrix? What is if this is something of these constant solutions? And actually, we were inspired because about a year ago, there was already like an algorithmic approach by this group where they solved the Yang-Baxter equation with some algorithm, and they found some non-regular difference form solutions. So we said, let's go, let's do them all, let's find them all. So how did we do it? As I said, we just had some expansion and we plugged it in. This is a tiny bit more detail. So as you might know, if you ever try to solve Yang-Baxter equations, it can get difficult, so you have to be a little bit clever. And our two clever moves that we did was do a change of variables from just uv to u minus v and u plus v. Then you can expand in just one variable instead of two. That already makes your life easier. And then instead of solving the whole Yang-Baxter, you just solve this set of necessary conditions, which you get by setting two of your spectral parameters to be equal, or setting u minus to be 0. Of course, if you solve this now, you'll have to in the end check that the Yang-Baxter equation is actually satisfied. But yeah, So you take your expansion, you plug it into your conditions, and you solve order by order. This is more or less what we did. And which kind of models did we find? Well, we found some full rank solutions, some diagonal ones, some of XY type, like here with Pauli matrices. We also found some difference form solution. That means here with just depending on the difference of spectral parameters. Otherwise, all of these Fs are just some general function. We also have some 8 vertex type solutions and some lower rank solutions. So our R matrices are not necessarily invertible. So you'll have here rank 3, but also rank 2 and even rank 1 solutions. Okay, you can in theory form charges with them. From the diagonal, you'll of course find diagonal charges. Here you might find some Hermitian charges. So far we have, but in quite generically, the charges you'd find would be long range. Okay, are there any very short questions about this classification? Otherwise, I'll switch gears a little bit and talk about relations between R matrices and lax operators. Okay, so this is just to remind you about the RLL, or fundamental commutation relation here, and why we care so much about it. So we care about it because if we have it, we can construct from it a tower of commuting charges, which is what we use to understand integrability. So at an integrability conference, we care very much about this relation. And if we look at it, we note, or we already know, that this is very similar to the Yang-Baxter equation. And also this lax operator is defined very similar to the R matrix. So what we wanted to do was we wanted to somehow rigorously denote these relations, these similarities. And we did this in these, this is 4 statements covered in how we denoted them in our paper, Proposition 3 and Theorem 1. Proposition 3 tells us that if we have a regular lax operator that satisfies this fundamental commutation relation, then the corresponding R matrix has to be regular as well. So you would have this regular, then you know this has to be regular as well. We proved this by simply expanding L, expanding R, plugging it in, and then doing some massages using permutation operators. So now you could ask, okay, this is nice, we know this now, that's nice that we proved it. You could ask, could you do this with non-regular as well? Could you basically ask, let L be a non-regular lax operator that satisfies this, thus R also has to be non-regular. And you could assume, okay, maybe because we use the permutation operators a lot, maybe not. And actually, we have, you can even find counterexamples to such a claim. That means you could say, you could have here a non-regular L matrix and find a regular R matrix that satisfies this, which is weird and unexpected, but that's kind of the headline of non-regular R matrices. The next 3 statements that we found are kind of all baked into this Theorem 1, which says that if you have an R matrix that satisfies the RLL relation and L is regular, then R will also satisfy the Yang-Baxter equation. Furthermore, it will also satisfy braiding unitarity, and there is a direct correspondence between those R satisfying the Yang-Baxter and the lax operators. So for obvious reasons, I'm not going to prove all of these things now. But again, you will have to do a lot of massages using permutation matrices, which you, again, could not do if you had non-regular lax operators. So if you tried to make a statement like this for non-regular laxes, it would look something like, your try would look something like this. take a non-regular Lax operator and try to solve your RLL relation for some unknown R. What you might find is an R matrix that doesn't solve the Yang-Baxter equation. Perfect. Instead, it might satisfy something like this, which we called the modified Yang-Baxter equation, with this M just being some big matrix depending on all spectral parameters, and which we had not found up until now that it satisfies any cute relation or equation. It's also fixed, like for a given R tilde, M would be fixed. So this brings us to my outlook and takeaway. So the takeaway is that all the existing formalism works like a charm for regular models. We proved a lot of things that we have had a gut feeling would be true anyways, but we also showed that once things are not regular, all of this gut feeling kind of breaks down and proofs don't work anymore and relations don't work anymore. Because of that, it would be very interesting to find some kind of formalism that does work in a regular setting. It would be interesting, maybe we could find models that are in blockwise regular, maybe we could find local charges there. If not, it would be also interesting to look more at these models that are inherently long range and see if we could find non-trivial models there. And then, of course, we could always come back to this modified Yang-Baxter and see if we could reformulate it in a more appealing way. Okay, that's it for me. Thank you for listening.
Thank you very much. Are there any questions? Yeah, Kolya? Oh, okay. No one listens to me, obviously.
Yeah. Thanks for the talk. I was wondering, so this modified Yang-Baxter equation, if I take a classical limit, is it like the modified classical Yang-Baxter equation that defines?
No, so far we were not able to map this because there has been we have not been able to map this to the modified classical. There has been other questions also in this direction, could you find this to be related to the trapezoid tetrahedron equation? Could you map this somehow to a dynamical or twisted? No. So far, no.
How many out of this 4x4 solutions you found would build up some unitary evolution?
So far, these two build up symmetric charges, Hamiltonians. None of the rest were either Hermitian, symmetric, antisymmetric, nothing of this sort.
I have a question about the solution of Yang-Baxter. So your solution is based on the statement that you can tailor expand your solution around the constant one, right?
Yeah.
But why is this true for any solution to Yang-Baxter?
You're asking if this is true for any solution?
Yes.
I mean, as long as it's analytic and differentiable, maybe you could come up with something really weird.
Okay.
Anything else? Yeah?
So this is not a question, but more a comment to the previous comment. I mean, generally, you can assume there is some region in the complex plane where the solution is analytic. And then when you can tailor expand there, and generally you can always resum the solution back up to some solution which may in general be complicated, like some square root structure or something like this. But I mean, this assumption of regularity is not really much of a restriction at all.
Okay, thank you. Was it the ones that is it this one that you mean, or is it a different one?
Oh.
So no, they do the regular solutions. We focus here on the non-regular ones. So all their solutions reduce to the permutation operator, but at higher rank. So these are different.
Okay, maybe we'll stop here and we can ask more later if you have questions. Thank you very much, Fedor. Okay, so our next speaker is Anders Wahlberg. He's going to be talking about orientifolds, cross-caps, and integrability in N=4 super Young-Mills theory.
Thank you. So I would like to thank the organizers for giving me this chance to talk. Before I go into this complicated business of orientifolds, I thought maybe first I would talk about a slightly simpler case, which luckily Charlotte already covered earlier today. So this is this duality between probe D branes in the ADS5 x S5 geometry. On one hand, adding defects to N=4 super Young-Mills on the dual side, and the so-called matrix product state on the PSU 2,2/4 spin chain, or in general some other boundary state on the spin chain. And what has been found previously is that all these three sides are related very nicely. You can map observables in one to observables in the other. And this has been explored over the last 10 to 15 years, and we found very good agreement on all three sides. Now, what we wanted to do was extend this study to another set of objects in string theory, which is the orientifolds. So these are much less studied than D branes in general. They share some of the same features. They carry tension. They are extended objects in various dimensions. But they're also different in many ways. They're non-dynamical. The tension can often be negative. And they're only really understood in perturbative string theory. So it'd be nice to have some setup like ADS5 x S5, where you can actually go away from the perturbative regime of string theory. But what is the dual of these? Well, one hint comes from the fact that orientifolds can also be interpreted as crosscaps on the world sheet. And that word crosscap came up in a different setup, which is that of N=4 super Young-Mills on projective space. So in general, if you take a CFT and place it on projective space, that's known as a crosscap CFT. And it shares many of the same features as a defect CFT. You break some conformal symmetry, you get new observables, you get cross ratios appearing already in the two-point function, and so on. And then what would be the natural candidate for a spin chain dual of this? Well, that would be that of the crosscap state. So whereas the matrix product state I had on the previous slide sort of entangled nearby sites on the spin chain, this crosscap state entangles sites on opposite ends of the spin chain. So it's sort of long-range entangled. But what we wanted to figure out is, are all these three things actually related, or is it somehow, they're all called crosscap, but they actually have nothing to do with each other? And in particular, that requires some specific setup for this N=4 theory. That's a bit non-trivial. So for this talk, I'll focus mostly on the n equals 4 side, but I'll comment on the two others as we go along. So what is this theory on the projective space? Well, the idea is you identify points that differ by a conformal inversion. So here we have some point x, and we identified with the point x prime that differs by a conformal inversion. And so if you have some operator located at x, you should identify it with an operator located at x prime, and this operator will not be the same operator, but modified ever so slightly in a way I'll come back to in a second. And this breaks conformal invariance, so now you only have an SO5 symmetry. Note here that maybe some of my time-like directions are slightly different from what you're used to seeing because we're working in a Euclidean setup here. Now it turns out that if you want this to be half BPS, you also need to break R symmetry. Again, this is similar to what people know from the defect cases. But maybe more non-trivially is that to have a nice integrability interpretation, it turns out that we need to also break gauge symmetry from SUN down to SON via a certain charge conjugation. And what that tells us concretely is that if you take some scalar Z, we should identify this sort of Z prime will not be Z itself. There will be some conformal factor, 1 over x squared. There will be a bar, which comes from this breakdown of R symmetry. And there will be a transposition, which comes from this breakdown of gauge symmetry. Now that looks a little bit puzzling. I'll come back to why this is natural in a second. But let's first see what some of the consequences of this are. So first of all, propagators in this cross-cap theory are slightly modified. So if you work in a free theory, you can normally derive propagators just as Wick contractions. But here it's slightly different because you now also need to consider Wick contractions not just between your two operators, but also between your operator and the mirror image of your operator, this O prime. And because the mirror image has this transposition, you get these sort of twisted propagators that twist as they go along. Okay? Now, if you then try to compute one-point functions in the theory at tree level, they just come from Wick contraction. And you find that they are actually order 1 in n. They don't scale with n. And if you work at tree level and to leading order, they're actually very easy to compute. It turns out there's one unique diagram that contributes. And the way it works is that you arrange your operators around in a circle like this, corresponding to their color structure. And you then Wick contract operators on opposite ends of the circle. And you can check that this is the only diagram that contributes at leading order. So for example, here I have 6 operators, and you'll find that I have 3. So here the colors each correspond to one loop in the diagram in the n factors. So here we have 3 loops, and that's the leading contribution. Okay? Now that diagram should look kind of familiar from my previous slide. This is how you see in n equals 4 that you get the cross-cap state on the spin chain, right? So here we were identifying sites on operators on opposite ends of this circle I drew, and in the cross-cap state we should do exactly the same. We should identify sites on opposite ends of the spin chain. And this setup turns out to be integrable. So if you want to compute these one-point functions, it can be mapped precisely to the overlap between a beta state and your cross-cap state on the spin chain. Very similar to what Charlotte was showing for this defects case, where here instead of the cross-cap state, we had this so-called boundary state. Now, for bosonic spin chain, it turns out that this overlap is given just in terms of this superdeterminant. So maybe you remember Shuta's talk from 2 days ago. He had all these complicated factors in front of the superdeterminant. Turns out that they are not there for bosonic cross-cap. But we're not so lucky that they're never there. If you go to a super spin chain, they do appear, and they're actually even more complicated. So for the experts in the audience, they're not just ratio of Q functions. They are some more complicated object. But we can still try to write down a formula for them in general. Okay? So this was the spin chain side. What's happening on the string theory side? Well, there, the object in question is a probe O1 brane. And turns out that in this setup, this probe O1 brane is orthogonal to our stack of D3s that make up the n equals 4 theory. And we can even perform some naive matching in the BMN limit, although there's much more to be said about the orientifold side of this to understand it better. And also here, this mysterious transposition we had, this charge conjugation that was necessary, has a natural origin, which is that orientifolds are known to reverse churn pattern factors. So that comes from the fact that they reverse orientation. So they also flip around where your string starts, which deep range starts on and which it ends on. And that's the precise analog of this transposition we had earlier. So it's in fact quite natural. And that brings me to some further work we're doing. So these cross-cap CFTs can also be defined with fixed points. So the map I showed you earlier, this conformal inversion, had no fixed point, but we can allow for fixed point, and this new cross-cap defect mixed theory has features both of cross-cap CFTs and defect CFTs. They appear to be new, haven't been studied before, so we have proposed what their structure is in general, and also been exploring it for the ON model in particular as a simple example. And then one reason why we're interested in this is that if you now do this setup in n equals 4, it should correspond to orientifolds of various dimension in various orientations, all of which can now have a natural origin in n equals 4 Superyang-Mills, and we hope to also explore this and have a whole host of theories we can study. Thank you.
Any questions? Yeah, Kolya?
So in this cross cap, can you have like composite operator asymptotically sitting at the origin? Would it define some kind of anomalous dimension then?
Sorry, in what? You mean in...
Like send some operators to the origin, so they're like all in, and then another one is mapped to infinity?
You mean adding on top of the cross cap?
As I understood, you insert your operators one-point function, they just in some arbitrary location.
Mm-hmm.
But
yeah, so you can add.
But zero is special, right? Because map.
Yeah, so it's mapped to infinity under this map, but otherwise you can add operators at any point you'd like.
Mm.
So the cross-cap state you discussed, does it break supersymmetry?
Sorry?
How much supersymmetry does this state break?
It's half BPS.
Half BPS. And the chiral operators, do they have one-point functions or they are protected?
I couldn't tell you from the top of my head. I think in general, yeah. I think in general in this setup, I think you should expect all. Okay. We can talk about it afterwards. I'm not sure on the top of my head.
Yeah, let's discuss later.
Is there a reason why it's SON as opposed to SPN gauge theory?
No, you can also do SPN. This was just to make it slightly easier, but you will have both. And on the, it doesn't make a huge difference here. So there's still a very natural interpretation in terms of the spin chain. But in the string theory, this is then also in string theory, we know that there are different types of orientifolds with different signs of the tension, and we can allow for both in general.
Okay, thanks.
Any more questions? If not, let's thank our speaker again. And our next speaker is Nat Levin. And he's going to speak about convexity of scaling dimensions over conformal manifolds.
Thank you very much. So thanks a lot to the organizers for this very nice conference and for the chance to tell you about this work. So let me begin by showing you this plot, which some of you in the room are responsible for. So, we have these beautiful plots from integrability. So we should look at them and try and scrutinize them and see what we can learn from them. And one thing I want to point out is that these single trace scaling dimensions in plane n equals 4 appear to be monotonic functions of Toff coupling, empirically. And more than that, if you plot them as functions of lambda instead of square root lambda, they look concave. And that's actually a more fundamental property, because concavity implies monotonicity for functions that blow up like the positive power of lambda for large lambda. Okay, so it's kind of intriguing, and you can ask some integrability experts, why does this happen? I asked some of you actually over the last year, and I didn't really get satisfactory answers. So that's kind of what drove me into this project. And actually, you can see that this property persists at least for lightest operator at finite n. So this is the data we have from the bootstrap by Chester, Dempsey, and Pufu. And they sort of believe that these upper bounds are saturated because here they fed into the bootstrap these integrated correlator constraints. So you can see that each of these curves is the upper bound on the lightest unprotected scalar, where n goes from 2 to 11. In each case, I've drawn this black wall, which is the self-estual point. So the two sides of the wall are like reflections of each other. You can just look to the left of the walls, and you see that each curve looks concave on the left of the walls. Okay, so it's kind of tantalizing. So I'd really like to understand why that happens in n equals 4, but actually for some technical reasons, which I can mention later, odd space-time dimension is much simpler. So in this first part of the project, I'm thinking about similar question, but in odd space-time dimension. And so I'm thinking about unitary CFTs in odd space-time dimension with exactly marginal couplings. I'm thinking here about conformal manifolds. And I have additional technical assumption that there's no mixing in this low-lying part of the spectrum between operators with even integer gaps. But that doesn't really play a role. And the result is that for any choice of quantum numbers, delta, the dimension of the lightest unprotected scalar, is a concave function over the conformal manifold with respect to the Zamolodchikov metric. So that just means that its covariant Hessian matrix is negative semi-definite. And more generally, the sum of the lightest n scalars dimensions is a concave function. So that implies the result above by taking delta n to be the first unprotected operator and the previous ones to be protected. Where for me, protected just means that their dimensions don't depend on marginal couplings. So they're constant over the conformal manifold. So this is actually a rather natural result, because if you just take linear combinations of operators, it's a general fact that the sum of the lowest n eigenvalues is concave for any n. And we already see this kind of thing in CFT as a function of spin. So the dimension of lowest lying operator of a given spin is known to be a concave function of spin. And we know that the same thing is true as a function of charge, at least asymptotically for large charge. So here, it's a similar statement, but over marginal couplings. So we're talking about a family of CFTs. So we're going to learn from this about conformal manifolds, their global properties, and also about unprotected operators, which is sort of normally difficult to learn about. But let me try and give a very fast argument why you should believe this statement. So let's consider a two-point function of this lightest scalar O, with dimension delta, on the sphere of radius r. I take log of this quantity, and I take two derivatives with respect to a marginal coupling G. Here I'm just focusing on a single marginal coupling, which couples to some marginal operator, but this argument can be applied with multiple marginal couplings. So the derivative brings down integrated marginal operators, and on the right-hand side I get second derivative of delta. On the left-hand side, I get this variance type quantity. And so specifically, this is the variance of the integral of L in O vacuum. So basically, it's just a kind of trivial consequence of unitarity that this should be positive. But that's, of course, too naive, because this is divergent. There's UV divergence when operators hit each other. So we need to find a finite positive quantity. So okay, we should regularize. And you can easily handle the singularities where the L's hit the O's just by cutting out balls, small balls around the poles where those operators are inserted. And then I still have a variance of some modified operator. I just changed the integration range. But what's more difficult, and so that's still positive. But what's more difficult to handle is the singularity where the L's hit each other. But you can actually handle that by analytically continuing in the dimension of L. So as I take delta L away from D, away from marginality, and bring it back, I get something, you can actually show that you get something finite and positive, but it's not exactly what you started with. It's not exactly this second derivative. You can compute that there's a non-analytic piece living exactly at delta L equals D, given by a contact term, which provides this affine connection term. And that's exactly the term you need. They conspire together to give you something covariant, which is the covariant second derivative of the scaling dimension with respect to the marginal coupling. So in this way, you prove that, so you can do this with the Hessian matrix. So you add some indices. So you prove that the Hessian matrix is negative definite. So now let's test this. So the only example I know of in odd dimension where we really have access to unprotected data is this family of 3D n equals 2 theories with 3 chiral superfields and a cubic superpotential. It has strongly coupled fixed points, and the marginal coupling tau lives in CP1, mod by the discrete duality group S4. So a fundamental domain is one little triangle here. This theory was studied by Strassler a long time ago, and more recently by Baggio et al. And they used epsilon expansion and the bootstrap to get some approximations to low-lying unprotected scaling dimensions as functions of tau in this very nice paper. So here is their plot for the lightest flavor singlet dimension. And qualitatively, it looks like this is in tension with what I said, because this function has a minimum at tau equals 0, and its images under duality. But that's actually a singular orbifold point. It's a corner of the fundamental domain. And so that's sort of okay, something goes wrong there, but it needs to be that the second derivative is negative on either side. So the prediction is that it should be some kind of sharp cusp minimum. Right? The claim is that second derivatives are negative everywhere. So here I'm focusing on like some real slice. So let's test this. Well, here in black, I'm plotting their epsilon expansion, so exactly the same plot, now just along this real slice. They use data from d equals 4 minus epsilon. So I improved this epsilon expansion by also adding d equals 2 data and performing a two-sided pade. So those authors actually noted that something must be going wrong at tau equals 0 because this red dot is a bootstrap upper bound, which is not satisfied by their curve. So something's going wrong near that point. And indeed, including this extra data, I find this blue curve, which does go below the red dot, and has this expected singular behavior at tau equals 0. And I checked indeed that the covariant second derivative is negative everywhere along this real slice, as predicted. And you can actually see that the mechanism for this cusp is that there are additional marginal operators associated with symmetry enhancement at precisely that point, tau equals 0, and these lead to this singular behavior at that point. So we can also learn from this about the global structure of the conformal manifold. And while the usual law is that conformal manifolds of 3D CFTs should be compact, here I'm telling you that there's a whole bunch of concave functions, and actually smooth compact manifolds do not admit smooth convex or concave functions. So it must be that what happened on the previous slide is generic. Well, if this usual law is correct. So it must be that in odd space-time dimension, compact conformal manifolds must have singular points. So this is a sort of interesting, quite general conclusion coming from this result. So before wrapping up, let me give some outlook. So I'm also thinking about deriving similar results in even space-time dimension. And there it's a lot more complicated because marginal operators generically mix with the identity operator on the sphere. So things are just a lot more technically complicated. So in particular, it would be very interesting to understand the case of planar n equals 4, where something even more amazing happens. So there it's not just the lightest unprotected operator that's concave, but actually, as I showed you, all of them look concave as functions of lambda, all the single traces. So it's almost as if what's happening there is integrability says that each state is in its own superselection sector. It has its own quantum numbers. So it's sort of related to level crossing. You're able to apply this argument to all of them without without just landing on the lightest one. It would be interesting to explore the relation to CFT distance conjecture and also to get similar results in defect CFTs. So to summarize, in odd space-time dimension, the lowest scaling dimensions are concave functions over conformal manifolds, and compact conformal manifolds of odd-dimensional CFTs must have singular points. And I tested these statements in 3D n=2 theories. Thank you.
Thanks a lot. Are there any questions? Yeah, Nadav.
Yeah, so you mentioned it, so maybe you don't want to talk about it. Defect conformal manifolds are quite ubiquitous, and there are many that are compact, but maybe they correspond to homogeneous spaces, so actually all data is constant. So
yeah, there are these examples where all the data is constant, so there this is sort of trivially true. Yeah, do you have examples in mind where they're...
Yes.
Yeah, which examples? It has to be odd. I mean, for this to apply out the box, has to be...
It's line defects in ABJM.
Yeah, I think it would be really interesting to think about. But it should be like, I mean, for this argument to apply, it should be a local operator in the defect that defines the marginal coupling, that defines the marginal operator. So not a bulk operator. Yeah. Okay, well, maybe we can discuss.
Can I ask a question?
Sure.
Yeah, so in your argument, how does the dimension is odd play a role?
Yeah, so first thing is that in even space-time dimension, in general, there's a log divergence in the partition function on the sphere. And you can subtract this away, but it makes the finite piece ambiguous, which means that, I mean, that plays a role in this argument because that's how the two-point function is normalized. So you get extra contributions from like derivatives of the partition function. But these are now scheme-dependent ambiguous quantities. So you should assume a certain enough supersymmetry, actually, that this finite piece of partition function becomes well-defined. So in 4D and 2D, this is understood. So first, you need to assume a lot of supersymmetry. But second, you still have this confusing issue that marginal operators in even dimension are always violating my assumption that they're even integer gapped from the identity operator. And this means you can write down some counter terms where they mix on the sphere. So,
but do you expect the mixing can be absorbed by, like, here you add a connection term which absorbs some?
Yeah, I mean, it's not that I don't think this result can work in even dimension. I just think it's a lot more complicated. Okay. You know, here you need to pick some scheme and deal with divergences in a kind of reasonable way. And I think that can be done in even dimension as well. It's just a lot more complicated, and there are more contact terms you need to worry about.
In principle, it can work. Yeah, thank you.
Kolya, you had something?
So there's more like technical question. So you kind of use both hard sphere regularization and also dimensional regularization, but dimensional regularization, like in particular, probably breaks conformal symmetry. Is it not a problem?
Well, yeah, I think you could probably do all of this with just dimreg. It's just that it's a lot simpler actually if you also cut out these balls. I think if you just did this kind of dimreg, it would also work. You're saying this. I mean, I'm just taking the integrals I have, and they depend on delta L, and then I'm just analytically continuing the value of delta L. So, yeah. Oh.
So could you remind what's wrong with applying this to ABJM and planar limit?
Well, the thing about planar limit, I mean, what's important here for making odd dimension simple is that the sphere partition function doesn't depend on marginal couplings. This you can show in general for a finite n, like for a genuine CFT in odd dimension, this is true. But in ABJM, you have dependence on n, which is discrete coupling, or discrete quantity. But dependence on n and k. But in large n limit, you now get dependence on their ratio, which you weren't supposed to have. I mean, that becomes marginal coupling, but so it kind of looks, in large n limit, it sort of behaves in this way more like an even dimensional CFT. In the sense that the partition function depends on this quantity which used to be discrete but is now marginal coupling. Maybe it's an interesting halfway house between. Yeah.
Okay, maybe we should leave it here, but very interesting. Thank you very much.
Thank you. Sorry, I dropped it.
Yeah, so the next speaker is, I don't know how to pronounce.
Beat Nayat.
Beat Nayat. Thank you. He's going to speak about beyond the tensionless limit.
Okay, so hello everyone. First of all, of course, thank you to the organizers for giving me the opportunity to speak about a series of works under the umbrella term of going beyond the tensionless limit. So this was done in collaboration with my supervisor Matthias Gabadil, Rajesh Gopakumar, and two master students, Dennis Kempel and Felix Lichtner. So what I mean by going beyond the tensionless limit is the following. Our starting point is this very well controlled and essentially provable instance of the ADS-CFT duality. So when you take ADS 3 times S 3 times T4, which has mixed flux, you turn off all the RR flux and you have minimal NS flux. It has been shown that this is the same as the 2D CFT symmetric product orbifold of T4. This manifests in a very pleasing way, but it is at a special point. For example, this tensionless string theory has a higher spin symmetry, and as soon as you turn on mixed flux, this can no longer be the case. It becomes quite difficult to study using worldsheet methods, but we know that it's the same as the CFT, and so this perturbation of turning on the RR flux is simply an exactly marginal coupling. And so we can study this perturbed CFT using the more well understood framework of CFT perturbation theory to understand the more general case and also maybe the CFT in its own right. As we heard in the morning, this might be of some interest. Okay, concretely what we want to do is understand how the algebra in this performed theory looks. And so we look at right-moving supercharges here and S tilde and how they act on quarter BPS states in this theory. These are characterized by being annihilated in the free theory. As soon as you turn on the coupling, there can be transitions, and in particular, these have anomalous dimensions. And when we look at the BMN limit, we see that this supercharge action has an effective description by a dynamical spin chain. Furthermore, our framework sort of allows us to study the conceptual question of how these geometric ADS 3 times S3 directions emerge from this 2D CFT. So this is what I will try to outline in the next few minutes, but to do it I have to introduce one of the best CFTs in the world, the symmetric product orbifold CFT. So when you take a CFT X, its symmetric product orbifold is obtained as follows. You take the CFT X n times, signified here by the lines, and then you mod out by the permutation group action. Concretely what this means is that in this CFT there are local operators called twist operators which implement a permutation action. So if you put the sigma here at this point and you read this diagram from left to right, you see that it implements the 1, 2, 3 cycle. If you take X equal T4, this theory has a tower of BPS states, which I call ket W. They are half BPS states, and in fact they are themselves twist fields. So they have this non-trivial permutation structure. As far as the spectrum is concerned, these are the analog of trace set to the J in n equal 4 super Young Mills. And just as in n equal 4 super Young Mills, BMN is taking J to infinity, here the BMN limit is taking W to infinity, and there are similar results in that original paper already for the string theory side. Okay, these states are protected, so to have something more interesting, we have to go one less BPS, which are the quarter BPS states, and they are actually descendants of these half BPS states. Schematically, they look as follows. You pack on all the fields you want, as long as they are left moving. This is a quarter BPS state. And these fields, these alphas are bosons, psi's are fermions, and they have a mode number p. These p are quantized in 1 over w. That's the free theory. Now this theory is perturbed by an exactly marginal coupling called phi. This is a descendant, a supercharged descendant of sigma 2, where sigma 2 is, big surprise, a twist field. It's a sum of all transpositions, and it's depicted here in the top right. can think of it as interchanging two colors. So when we have a quarter BPS state and we look at it in perturbation theory, what can happen at first order looks roughly like this. So you have this W state, and then you have one perturbation. If you imagine that these two legs eat these two legs, the last color is also permuted, and you transition to the W+1 sector. There's another planar diagram where these two legs eat adjacent legs, and it undoes a permutation on one of the legs, and you transition to the W-1 sector. So this perturbation theory actually already at first order has some sort of length changing effect. Okay, that's all we need to know. Now go back to the problem. We want to calculate how these supercharges act on quarter BPS states, and to be concrete and simple, I choose this quarter BPS state, which is just two bosons acting on the vacuum, the half BPS vacuum. To see how this S tilde can act on the state, you basically have to write down all the states it can transition to and calculate the transition elements. There's a quadrillion states, and it's but in this BMN limit there's a certain simplification, namely that the transitions to almost all of them are at least 1/W suppressed. And so if you want to look at how this supercharge acts, you can focus on the order 1 coefficients, and these are two states who are of a very simple form, namely S tilde takes one of the bosons, here the second one, turns it into a fermion. They can have a different mode number, so the Q's don't have to be the P's for now, and because of the length changing, this S tilde shifts the W up by 1. And these transition elements here, we can explicitly calculate in the perturbation theory. And I plot them on the next slide here. So this is this transition element as a function of Q1, which is the mode number of the boson. And what you see immediately is that they're all very small, and then they have extremely sharp peaks when Q1 gets close to one of the mode numbers of the initial of the bosons in the initial state. And so these points are spaced in 1/W. This is W300 or something. As you increase W, these peaks become narrower and narrower. And so effectively, as W goes to infinity, you want to describe this as follows, that S tilde eats the state, and it really, there's no sum over Q here anymore. It acts on the first alpha, turns it into a fermion with the same mode number P1, or it acts on the second alpha and turns it into a fermion, and it shifts the length by 1 upwards. And there's a coefficient here in front, which we calculate. So this is some sort of individual mode number conservation in this BMN limit. Okay, we can more effectively elegantly describe this by some commutator. So we prescribe the following commutator, that S tilde, the right moving supercharge, doesn't commute with the boson. Instead, it turns it into a fermion with some momentum dependent prefactor, and it inserts some Z plus, which we define by a length changing effect. Q tilde is the conjugate, and it acts as the conjugate. In particular, it lowers the length by 1. So to do this, we have to do some analytic continuation to get these coefficients, although we calculated them at finite W. This is sort of at infinite W. This prescription is consistent with the anomalous dimension and with the consistency of the algebra on shell. So this is exactly the same as in Nicholas's 2005 paper originally of this dynamic SU2/2 spin chain. Okay, if you give this prescription, you get a system which has an S matrix, and this S matrix satisfies the Young-Baxter equation. So it's integrable, and it was also found using worldsheet methods here. Also by self-consistency, you find an anomalous dimension for these magnons, which takes the square root form. In particular, the effect of the NS flux is that here is not a 1, but a p squared. And also this square root form was already found using semi-classical methods in these papers and others. All right, that's one part of the story. Another thing I want to talk about, so this is sort of infinite W. We can also look, since our method is calculating at finite W, we can look at large and finite W and study the following conceptual question, namely, okay, obviously 8 is 3 times S3 times T4 in light cone gauge has 8 geometrical directions, and the symmetric product orbifold of T4 has T4. So, okay, you might say the T4 goes with the T4, but what happens to the other 4 directions? And how do they emerge from the CFT? At least at strong coupling, they should be somewhat visible. The qualitative answer is the following. So as I mentioned, at the free point, you have this higher spin symmetry and everything is completely degenerate. You don't see any difference. But when you turn on the perturbation, this singles out some eigenvectors, and we see some qualitative differences in this large W limit. So I plot them here in a certain sector. These are the eigenstates made out of 2 fermions. And almost all of them look like the orange ones. So we call them short. They have coefficients which are peaked at select values of the mode numbers. Then there's exactly one state which combines almost all of the mode numbers together, which is shown here in blue. And when you look at the anomalous dimension of these states, they actually behave exactly like you would expect the BMN magnon in the S3 direction to do. They evade sort of the off-shell algebra analysis from before because they combine all of the states together. On the other hand, the short states behave like a 2 magnon state of the T4 directions. So this is our interpretation that that we can see from the eigenstates, we can see these geometric directions emerge. Okay, just to conclude, I've shown you a bit about the calculation we did in the orbifold in this BMN limit and how we saw that there is an off-shell symmetry algebra, a dynamical spin chain describing this supercharge action in that limit, some sort of integrable corner of this theory. And I've also quickly talked about the conceptual question of how you can see geometric directions of this ADS3 times S3 emerge from this 2D CFT, although there's a lot of open questions about this, which I would be interested to explore in the future. For example, since they're massive magnons, if they behave more analogously to ADS5 times S5 magnons. All right, thank you very much for your attention.
Questions?
Hi. So what about massless?
Yeah, so I would say, these ones are the massless ones. So also here, there's no m squared. So these are sort of the T4 magnons. They are made out of T4 orbifold fields. Also, sort of classically, the asymmetry generators of S3, which rotate the S3, they are SU2 affine algebra in the orbifold, and they are bilinears in the fields. So already there, they're not really independent. So these T4 magnons sort of form bilinears, which give you a single S3 direction. That's the qualitative way.
Other things? Someone at the back.
So am I understanding correctly that you're saying that S3 is actually more like a bound state of 2 fermion states?
Yes, I mean, I don't know exactly. So there's no sort of position space picture. I don't know in what sense it's a bound state, but yes, of course, yeah. Intuitively, I would also see it as a bound state of
I see.
I mean, also when you look at bound states of the S matrix, they sort of give the correct spectrum at least for what you would expect from massive directions.
Well, I guess perhaps you know, but like there is also something similar happening in GKP string.
I don't know, but maybe you can tell me later.
Well, I guess you can ask Benjamin.
Okay.
More things?
Questions? Arkady Zeitlin was raising his hand before.
Okay. Arkady?
So you started with saying something like you want to include Ramon flux, and then you considered some perturbation which you think is natural. So what's the evidence that that perturbation actually corresponds to inducing switching on Ramon flux on ADS3S3? So the evidence was like this BMN dispersion relation, or what's the evidence?
I mean, this is sort of an old matching of moduli. You have the moduli in the orbifold theory. 16 of them correspond to deforming the T4, and then there's 4 left which come from twisted sectors. You would imagine that your modulus has to come from the twisted sector to break this orbifold structure. And then there's a paper by Spentavadi and Justin David where they go through in more detail and analyze the charges and the symmetry, how these moduli transform under the global symmetries to propose this matching of the Ramond flux with this field. But yes, a posteriori, maybe also our dimensions are also an evidence for this.
What about the on string side? So you have your string description, then you can ask which operator corresponds to switching on Ramond flux, right?
Yes.
And that you can do in NSR kind of for hybrid formalism in principle.
Yes.
So that should correspond to that deformation.
Right, it does. So you can do it using the DDF construction. There's DDF operators, you basically take the dual to this state, and then you apply the DDF operators. According to these, you also have to do some worldsheet supercharges, whatever. You integrate over both, both coordinates, and it exists. But it's not a calculational advantage, I would say.
Anything else? Okay, looks like there are more questions for now, so thank you again.
Before we leave, just an announcement for those going to the conference dinner. You can either travel yourself, or we will go as a group from here at 5 p.m. and at 5 p.m. Okay, the dinner is at 6, and please remember to bring your dinner tickets. Again, as we mentioned, they are inside the badge. Yeah.